What if I told you that right now, scientists are openly discussing whether we're watching the flyby of an ancient advanced technology, a technology so advanced it could have only came from a civilization that died long before our sun was even born. But here's what's really unsettling. If this were a probe from an ancient civilization, designed to look exactly like a comet, how would we even know? So let's imagine something that sounds like science fiction, but sits at the edge of real research. The archaeological probe hypothesis suggests that Atlas isn't just an old rock. It might be a remnant from an extinct galactic civilization disguised as a comet, not recently extinct, not even extinct within the lifetime of our species, but extinct for billions of years before Earth even formed. This isn't just random speculation. When scientists trace Atlas backward through space, they find something unsettling. The object comes from what we call the galactic thick disk. These are stellar populations that formed over 10 billion years ago, during the early, chaotic period of our galaxy's evolution. Atlas predates our entire solar system by billions of years. Think about that timeline for a moment. When Atlas began its journey, our sun didn't exist. Earth was just scattered dust in a nebula that wouldn't collapse for another 4 billion years. Complex life wouldn't appear for billions of years after that. Yet Atlas was already travelling through space, carrying whatever secrets it holds from that ancient era. Now, when we say archaeological in this context, we don't mean old pottery or buried cities. We mean something far more profound. Archaeological implies that Atlas could be carrying information or technology from civilizations that rose, flourished, and vanished eons ago, like finding a message in a bottle, but the bottle has been floating in the cosmic ocean since before our world existed. The implications are staggering. If this hypothesis holds any truth, we're not just observing space debris. We're examining the fossilized remains of intelligence itself. Intelligence that solved problems, built things, perhaps even explored the galaxy, all while our corner of space remained empty and dark. But here's the question that keeps researchers thinking. After billions of years in the harsh environment of interstellar space, how would we distinguish between ancient natural material and ancient artificial material? Radiation breaks down complex molecules, cosmic dust sandblasts surfaces, gravitational interactions can tear objects apart. Any obvious signs of technology would have been erased long ago. Consider the persistence problem. Small objects shouldn't last intact across such vast timescales. They should be destroyed by collisions with dust grains, worn away by radiation, torn apart by gravitational forces. The fact that Atlas has survived feels almost unreasonable, unless its durability comes from design rather than chance. If Atlas originated from the thick disk, its builders would have understood something we're just beginning to grasp. The galaxy is violent and unstable. Stars explode. Black holes devour matter. Radiation floods space. Any probe designed to last billions of years would need to be engineered for survival on scales we can barely imagine. Those design choices would be invisible to us now. They'd be buried under what looks like natural cometary crust. The original structure might be unrecognizable, worn smooth by eons of cosmic weathering. What we see might be the equivalent of finding a smartphone after it's been tumbled in a river for 1 million years. The shape changes, but the core might remain. The timescales involved challenge everything we think we know about civilizations. Think about human history. Our entire recorded civilization spans maybe 10,000 years. Advanced technology covers barely 2 centuries. Now multiply that by 1 million. What could a civilization accomplish in 10 billion years? What could they build? Where could they go? They could have flourished, evolved beyond biology, transcended their homeworlds, and spread across the galaxy. They could have developed technologies we can't even imagine. They could have sent out thousands, maybe millions of probes like Atlas. Then they could have disappeared, leaving only these silent messengers to mark their passage. But here's the haunting part. If such civilizations existed, they would have known that the galaxy changes. Stars die. Planets become uninhabitable. Species go extinct. They might have designed their probes not just to explore, but to carry forward some record of what they were. A kind of deep time archaeology project, preserving knowledge for whatever intelligence might eventually arise to find it. And yet, we're left with the fundamental problem of proof. How do you test for intelligence that's been processed by billions of years of cosmic evolution? The probe would have been designed to look natural. Its builders would have known that obvious artificial signatures wouldn't survive the journey. The very success of their camouflage makes detection nearly impossible. We're like archaeologists trying to study a civilization so ancient that all their cities have been ground to dust, all their metals have corroded away, all their distinctive features have been worn smooth by time. What we find might look indistinguishable from natural rock, even though it once held libraries of knowledge. The really unsettling possibility is scale. If Atlas represents this kind of archaeological remnant, it might not be alone. The thick disk produced countless stars, and if even a tiny fraction developed intelligence, they could have filled the galaxy with these messengers. We might be swimming in ancient technology without recognizing it. Every meteorite, every piece of space debris, every unusual object could potentially be carrying traces of vanished civilizations. The natural and the artificial become indistinguishable after enough time passes. It's like trying to find fossil footprints in rock that's been heated, crushed, and reformed a dozen times. The archaeological interpretation forces us to confront an uncomfortable truth about our place in cosmic time. We think of ourselves as relatively advanced, as the current pinnacle of intelligence in our local region of space. But if Atlas is what some suspect, we might be newcomers examining artifacts left by civilizations that achieve things we haven't even dreamed of yet. These hypothetical builders would have watched their stars age and die. They would have seen their planets freeze or burn. They might have evolved beyond physical form entirely, leaving only their machines to continue the work. Atlas could be one of those machines, still functioning after all these eons, still carrying out a mission programmed when our sun was just a distant possibility. But we need to be clear about something important. While the age calculations for Atlas are solid science, the archaeological interpretation remains pure speculation. We have no direct evidence that Atlas contains artificial components. No signals, no unusual structures, no materials that can't be explained by natural processes. The hypothesis emerges from the convergence of strange factors, the improbable survival time, the unusual chemistry, the precise trajectory, the timing of its arrival during our brief window of technological awareness. Each factor alone could be natural. Together, they create a pattern that makes some researchers wonder. What we do know is that Atlas carries information. Whether that information is chemical records of stellar formation or data from vanished civilizations, it represents knowledge from an era we can barely imagine. The object has travelled farther through space and time than anything else we've ever studied. If questions like these are your kind of thing, please consider tapping the like button so others can find it too. From here, we need to examine another disturbing possibility. What if Atlas isn't just carrying ancient technology, but represents something more deliberate, more calculated than a simple archaeological remnant? What if the most dangerous thing about Atlas isn't what it appears to be, but what it's designed to hide? Think about the original Trojan Horse. Troy's defenders saw a wooden gift left behind by retreating enemies. They welcomed it inside their walls, never suspecting warriors waited within. Now imagine that same deception, but executed by a civilization with billions of years to perfect the art of disguise. Atlas arrives during humanity's first era of advanced space telescopes and planetary defense networks. The timing feels almost orchestrated. We've developed just enough technology to detect and study interstellar visitors, but not enough to truly understand what we're seeing. It's as if something waited for us to build the right instruments before making its appearance. But the most unsettling part isn't just what Atlas shows us, it's what it hides. Imagine designing a probe not to reveal technology, but to erase its fingerprints entirely. Every sensor, every circuit, every chamber would be wrapped in layers of ice and dust. Instruments would remain invisible, entombed inside a shell that looks and behaves like a comet. A Trojan horse is not powerful because of what it shows, but because of what it conceals until it's too late. Consider the patience behind such a strategy. A probe could drift silently for eons, waiting until it stumbles across a system with intelligent life. To us, it appears accidental, a random flyby. But from the inside, it could be a reconnaissance sweep, an uninvited survey that leaves no trace of its true function. Camouflage is most effective when it does not just imitate nature, but when it becomes indistinguishable from nature itself. Atlas forces us to ask whether our instruments are actually detecting a comet, or whether they're watching a machine perform a perfect impersonation. Atlas moves at over 137,000 miles per hour. Even by interstellar standards, this speed is extraordinary. The sun's gravity cannot slow it down or capture it. This is a one-way journey through our solar system, executed at precisely the velocity needed for optimal data collection, without gravitational interference. The trajectory raises statistical questions that make astronomers uncomfortable. Atlas passes remarkably close to Venus, Mars, and Jupiter during its flyby. The probability of such a path occurring by random chance measures approximately 0.005%. Natural stellar ejection rarely produces trajectories that allow observation of multiple planets in a single pass. Think of it like a river cutting through rock layers. Each layer tells a story about different geological periods. But if you found a river that somehow managed to expose every significant rock formation in perfect chronological order, you might start wondering if someone planned that route. Atlas's path reads like a surveyor's dream trajectory. The timing of Atlas's arrival corresponds with another curious detail. It entered our solar system's outer reaches roughly 8,000 years ago. That time frame aligns with humanity's development of complex civilizations, metallurgy, and organized agriculture. The correlation might be coincidence, but it adds to the pattern of convenient timing. Space agencies maintain careful language when discussing Atlas's anomalies. Press releases focus on the scientific value of studying interstellar material. They emphasize Atlas's contribution to our understanding of stellar formation processes. But researchers familiar with the data speak more cautiously in private conversations, acknowledging uncertainties they cannot explain publicly. The discovery timeline itself raises questions. Pre-discovery images show Atlas was trackable weeks before any public announcement. Professional observatories had time to study the object's behavior and chemical signatures before revealing its existence. This delay creates perfect cover for withholding the most revealing data from public analysis. Limited observation windows conveniently restrict independent verification. Amateur astronomers and smaller institutions cannot conduct their own detailed studies. The brief visibility period means we depend entirely on major observatories for our understanding of what Atlas actually is and what it's doing. If Atlas were carrying dormant technology, biological samples, or surveillance equipment within its icy nucleus, we might never know. The materials could wait for specific activation conditions. Solar heating might trigger systems that have remained inactive during billions of years of interstellar travel. Components designed to mimic natural sublimation would be virtually impossible to distinguish from actual comet behavior. A truly sophisticated probe would anticipate our detection methods. It would generate exactly the electromagnetic signatures we expect from natural objects. It would avoid radio emissions that might reveal artificial origins. It would behave precisely like a comet should behave, while secretly accomplishing entirely different objectives. The forward particle buffer Atlas creates resembles something else entirely. Most comets trail debris behind them as they move through space. Atlas projects material ahead of its nucleus, creating a cloud of particles between 1 and 10 micrometers in size. This could function as obstacle detection during high-speed interstellar travel, or as a sensor array gathering data about our solar environment. Consider the engineering challenge of designing a probe to survive billions of years in deep space, while maintaining operational capability. The shell would need to protect delicate instruments from cosmic radiation and micrometeorite impacts. It would require power systems that remain functional after eons of dormancy. It would need communication methods that leave no detectable traces. Natural selection produces remarkable camouflage in Earth's ecosystems. Stick insects mimic twigs so perfectly that predators cannot distinguish them from actual branches. Leaf insects recreate the exact patterns and coloration of their plant hosts. If evolution can produce such sophisticated deception in a few million years, imagine what deliberate engineering might accomplish over billions. The archaeological probe theory suggests Atlas carries information from civilizations that existed before our Sun formed. But the Trojan Horse hypothesis proposes something more immediate. Instead of passive data storage, Atlas might house active systems designed to study our current civilization while maintaining perfect concealment. We assume that advanced civilizations would announce their presence or make contact deliberately. But what if survival in a potentially hostile galaxy requires absolute stealth? What if civilizations that reveal themselves too early become targets for more aggressive species? The dark forest theory suggests that silence itself might be the signature of true intelligence. Atlas tests our ability to distinguish between natural phenomena and sophisticated artifice. Every anomaly that supports the probe hypothesis could also result from formation in exotic natural conditions. The unusual chemistry might reflect stellar environments unlike anything in our local galactic neighbourhood. The precise trajectory might emerge from complex gravitational interactions we don't fully understand. Yet the convergence of factors creates a pattern that stretches credibility. Convenient timing, optimal trajectory, suspicious chemistry, and restricted observation windows. Each element alone might seem unremarkable. Together they form a picture that makes even skeptical researchers pause and consider extraordinary possibilities. The Trojan Horse scenario remains speculation without direct evidence of artificial components or deliberate deception. We cannot peer inside Atlas's nucleus to examine its internal structure. We cannot detect the electromagnetic signatures that might reveal hidden technology. We cannot distinguish between controlled releases and natural sublimation without prolonged observation that Atlas's speed makes impossible. But Atlas forces us to confront an uncomfortable question. If we received a visit from a truly advanced reconnaissance probe, would we even recognize it? Or would we see exactly what it wanted us to see? A harmless interstellar wanderer that poses no threat to our world or our assumptions about our place in the cosmos. If the disguise theory holds, the real evidence won't be in Atlas's shape or its path. It will be in the gases it exhales, the invisible fingerprints it leaves trailing behind. Atlas isn't just behaving strangely, it's exhibiting a chemical signature that reads like a textbook on how to build a stealth probe. The James Webb Space Telescope revealed something that should make us pause. Atlas shows an 8:1 ratio of carbon dioxide to water. That's the highest ever recorded for any comet by a wide margin. Normal comets from our solar system show roughly equal amounts of these two substances. This extreme imbalance defies every model we have for how comets form naturally. But the carbon dioxide anomaly is just the beginning. Atlas releases atomic nickel vapor without any accompanying iron. In nature, these two elements are forged together in supernovas. They travel together through space. They appear together in meteorites. They're found side by side in virtually every natural formation we've studied. Yet Atlas somehow releases nickel while keeping iron locked away. Atomic nickel requires extremely high temperatures to exist in gaseous form. We're talking about internal heating that operates independently of solar radiation. Atlas maintains these conditions while drifting through the cold of deep space. This suggests mechanisms that don't match any natural comet behaviour in our records. The mystery deepens when you examine how these emissions change. As Atlas approaches the Sun, both nickel and cyanide production shoot up steeply. much faster than simple ice melting would predict. The pattern looks more like a controlled release system responding to external conditions than natural sublimation responding to solar heat. Think of it like a thermostat that's been programmed to release specific materials at precise temperatures. Natural comets warm gradually and release materials in predictable ratios based on their composition. Atlas responds with sharp increases in exotic gases that follow no known natural pattern. Cyanide gas adds another puzzle piece. This toxic compound appears in Atlas's plume alongside the nickel, creating a chemistry profile unlike any catalogued solar system comet. The combination suggests formation processes or material compositions that don't exist in our neighbourhood of space. Here's what makes the disguise hypothesis so unsettling. If you wanted to build a probe that could pass as a natural comet, you'd need to engineer materials that would outgaze convincingly under solar heating. You'd want chemical signatures that seem natural enough to avoid suspicion, but exotic enough to be explained by alien stellar formation conditions. Atlas's chemistry reads exactly like that kind of engineered camouflage. The extreme carbon dioxide ratio could be explained by formation in regions where CO2 ice was abundant and water was scarce. The nickel without iron could indicate unknown natural processes in foreign stellar environments. Every anomaly has a plausible natural explanation that keeps it just within the realm of possibility. But when you stack all these anomalies together, the pattern becomes harder to dismiss. It's like finding a rock that's the perfect weight, the perfect shape, and the perfect hardness to be used as a hammer, but claiming it formed that way by accident. Each individual trait might be coincidence, but the convergence suggests intention. The rapid gas production creates another engineering-like signature. Instead of steady sublimation as the object warms, Atlas shows controlled bursts that accelerate beyond what simple heating would produce. This behaviour resembles active venting systems more than passive ice melting. It's as if internal mechanisms activate when external conditions reach specific thresholds. The temperature requirements for nickel vapour create their own mystery. Natural comets don't maintain the internal heat needed for continuous nickel emission. Atlas does this while moving through space far from any external heat source. This points to energy storage systems or chemical reactions that we don't see in normal comets. What's particularly striking is how these chemical releases coordinate with each other. The nickel, cyanide, and carbon dioxide don't just increase randomly as Atlas approaches the Sun. They follow patterns that suggest interdependent systems rather than independent ice deposits melting at different rates. If Atlas were designed to mimic natural comet behaviour while carrying out a different mission, this chemistry profile would be nearly perfect. Exotic enough to be explained by alien formation conditions, but not so exotic as to be obviously artificial. The kind of sophisticated camouflage that could fool our instruments while maintaining operational capability. The alternative explanation requires us to accept that Atlas formed under natural conditions so unusual they don't exist anywhere in our solar system or in any of the hundreds of comets we've studied from our local environment. Conditions that would separate nickel from iron, create extreme carbon dioxide concentrations, and maintain internal heating systems across billions of years of interstellar travel. Both explanations strain credibility, but in different ways. The artificial explanation requires accepting that advanced civilizations exist and have the technology to create perfect comet mimics. The natural explanation requires accepting formation conditions and physical processes that we've never observed despite decades of studying comets, asteroids, and interplanetary chemistry. The timing of these chemical releases adds another layer to consider. Atlas begins intensive outgassing just as it enters the range of our most sensitive instruments. It maintains this behaviour through the period when we have optimal observation conditions, then will presumably return to dormancy as it exits our solar system. The schedule seems almost designed for maximum data collection during our brief observation window. What makes this particularly unsettling is how the chemistry changes create exactly the kind of signature that would allow a probe to study our solar environment. The forward particle buffer acts like a sensor array, sampling conditions ahead of the main body. The controlled gas releases could be testing atmospheric composition and solar radiation levels. The internal heating maintains operational temperature for sensitive equipment. Each chemical signature Atlas displays has been observed individually in natural objects under extreme conditions. High carbon dioxide ratios exist in some outer solar system objects. Nickel vapor appears in certain types of meteorites. Rapid outgassing occurs during close solar approaches. But the combination and timing create a profile that doesn't match any natural formation scenario in our database. The question becomes whether we're seeing the breakdown of artificial materials under solar heating, or natural chemistry from stellar formation conditions unlike anything in our experience. Both possibilities expand our understanding, but in dramatically different directions. If Atlas formed naturally, it tells us that interstellar space contains formation environments radically different from our local region. Chemical processes that separate elements we thought were inseparable. Heating mechanisms that maintain temperature across billions of years. Composition ratios that fall far outside our models of how planetary systems evolve. If Atlas is artificial, it demonstrates technology sophisticated enough to maintain operational capability across interstellar distances and geological timespans. Material science advanced enough to create perfect natural camouflage. Engineering precise enough to coordinate complex chemical releases with external environmental changes. Either explanation forces us to revise fundamental assumptions about what's possible in our galaxy. Natural Atlas means our models of stellar formation and planetary chemistry are incomplete. Artificial Atlas means we're not alone, and that intelligence has achieved capabilities we're only beginning to imagine. The chemical evidence alone can't resolve this question definitively. Unusual doesn't automatically mean artificial, just as artificial doesn't automatically mean threatening. Atlas could be a natural object from formation conditions we don't understand, or an artificial object on a mission we can't comprehend. What the chemistry does tell us is that Atlas represents something genuinely unprecedented in our experience. Whether natural or artificial, it carries information about processes and possibilities that expand our understanding of what exists in the universe beyond our local environment. The chemistry shows us Atlas is more than it seems, but chemistry alone may not be the end of the mystery. What if those exotic gases are not disguise at all, but delivery systems waiting to activate? What if Atlas isn't just chemically strange? What if its unusual composition is actually a carefully engineered delivery system, carrying the most dangerous cargo humanity has ever encountered? The payload hypothesis suggests that Atlas's anomalous chemistry isn't natural formation, but evidence of deliberate engineering designed to transport something lethal through interstellar space. Those controlled gas releases we discussed aren't sublimation responding to solar heat. They're testing delivery systems after billions of years in deep freeze. Consider what could survive an interstellar journey lasting 7 billion years. Frozen pathogens engineered to activate under solar warmth. Biological weapons designed to target systems they've never encountered. Organisms that remain dormant in the absolute cold of space, waiting for the right temperature triggers to begin reproduction. Atlas's core could harbour microscopic threats protected by layers of ice and rock. The carbon dioxide-rich environment creates perfect preservation conditions for biological materials. Low oxygen, stable temperature, protection from cosmic radiation. It's like a natural cryogenic storage system designed to keep samples viable across geological timespans. The temperature increases as Atlas approaches our inner solar system don't just melt ice. They could activate dormant biological systems that have been waiting billions of years for the right conditions. Engineered pathogens that begin reproduction when they detect the chemical signatures of a life-bearing solar system. But biological threats represent only one possibility. The nanotech seed scenario presents an even more unsettling option. Self-replicating molecular machines dormant in Atlas's nucleus, waiting for raw materials to begin exponential reproduction and planetary transformation. These microscopic devices could be designed to remain inactive during the interstellar journey, then activate when they detect the heavy elements and complex chemistry found near stars with planetary systems. Once triggered, they begin converting available matter into copies of themselves, spreading through space like a technological virus. The forward particle buffer Atlas creates isn't just unusual comet behaviour. It could function as an active dispersal system, spreading microscopic payloads across millions of kilometres as it approaches our inner solar system. Each particle in that buffer zone becomes a potential delivery vehicle for whatever Atlas carries in its core. Think of it like dandelion seeds carried on the wind, except these seeds are engineered to survive in the vacuum of space and activate when they encounter the right environmental conditions. The buffer extends Atlas's effective range far beyond its physical boundaries. The timing creates another layer of concern. Atlas's outgassing begins precisely when it enters the range where those particles could reach Earth's orbital path. The controlled releases accelerate as Atlas moves closer to optimal dispersal distance. It's as if internal systems recognise when conditions are right for payload delivery. Major space agencies monitor Atlas's chemical output with unusual intensity. Public reports focus on the scientific curiosity of exotic chemistry, while sanitising discussions of potential contamination risks. Press releases emphasise the safe distance and natural explanations, while internal communications may address more concerning possibilities. The careful language used in official statements suggests awareness of scenarios they're not discussing publicly. References to remote observations and protective protocols hint at precautions taken against unspecified risks. The coordination between multiple agencies indicates preparation for possibilities beyond simple scientific observation. If Atlas carries engineered threats, Earth may already be in the contamination zone without any way to detect or neutralize the danger. Those microscopic particles travel at interplanetary speeds, invisible to our detection systems, potentially carrying payloads we lack the technology to identify or counter. The dispersal timeline means contamination could precede recognition by months or years. Biological agents might establish themselves in our environment before we understand what's happening. Nanotech systems could begin reproduction cycles using terrestrial materials while remaining below our detection thresholds. Current planetary defense systems focus on deflecting large impactors. We have no protocols for dealing with microscopic threats dispersed across millions of cubic kilometers of space. No filters to screen interplanetary contamination. No early warning systems designed to detect biological or technological infiltration. The detection challenge becomes even more complex when you consider that advanced payloads would be designed to avoid recognition. Biological agents engineered to mimic natural microorganisms until activation. Nanotech devices programmed to remain dormant until they achieve sufficient numbers for coordinated action. Atlas's extreme velocity compounds the threat assessment. At those speeds, any payload dispersal occurs faster than our ability to track or respond. By the time we recognise contamination, the source has already passed beyond our reach and the dispersal pattern has expanded beyond any possibility of containment. The interstellar origin adds another dimension to the payload hypothesis. Materials from other stellar systems could carry biological or technological threats that evolved under completely different conditions. Pathogens adapted to alien biochemistry, but capable of exploiting terrestrial biology in unexpected ways. These threats wouldn't follow terrestrial evolutionary patterns or respond to terrestrial countermeasures. Antibiotics developed for Earth-based bacteria might prove useless against organisms that evolved around different stars. Immune systems shaped by 4 billion years of terrestrial evolution could be helpless against alien biological systems. The engineering required to create viable interstellar payloads suggests technological sophistication far beyond our current capabilities. Civilizations capable of designing delivery systems that function across billions of years and interstellar distances possess capabilities we're only beginning to imagine. Such advanced engineering might produce threats we lack the conceptual framework to understand or counter. biological weapons that operate on principles we haven't discovered, nanotech systems that use physics we haven't mastered, payloads that exploit vulnerabilities we don't know we have. The payload scenario connects to larger questions about galactic ecology and civilizational survival strategies. If advanced species routinely seed other systems with biological or technological agents, the galaxy becomes a much more dangerous place than our isolation has led us to believe. Interstellar contamination could represent a standard phase in galactic evolution. Civilizations reach technological maturity, develop interstellar dispersal capabilities, then systematically seed other systems with their biological or technological legacy. Atlas could be part of a galaxy-spanning contamination network that operates across deep time. The silence Atlas maintains in radio wavelength supports, rather than contradicts the payload hypothesis. A delivery system designed to avoid detection wouldn't broadcast signals that reveal its artificial nature. It would maintain perfect comet camouflage until payload release, then continue silently toward its next target system. Even the trajectory geometry suggests payload optimization. Atlas's path provides optimal dispersal angles for reaching multiple planets in our system. The retrograde approach ensures maximum coverage of orbital zones, where life-bearing worlds are most likely to exist. The chemical releases create ideal conditions for payload activation and dispersal. Carbon dioxide provides chemical energy for biological systems. Exotic gases could serve as activation triggers for dormant technologies. The controlled timing ensures payloads deploy when environmental conditions optimize their survival and reproduction. But the payload scenario faces the same evidential challenges as other extraordinary explanations for Atlas's behavior. We detect unusual chemistry and strange physics, but nothing that definitively indicates biological or technological components. The absence of obvious artificial signatures could support either interpretation. Natural objects don't emit technological signals because they're natural. Sophisticated artificial objects don't emit obvious technological signals because they're designed to avoid detection. Advanced payload systems might be indistinguishable from natural phenomena using our current detection methods. We lack the instruments to identify microscopic biological threats or nanotech systems operating below our resolution limits. The payload hypothesis represents our darkest fears about interstellar contact played out on a cosmic scale. The possibility that first contact comes not through communication or visitation, but through contamination by weapons or agents we can't detect until it's too late. Yet this scenario remains pure speculation without evidence of active biological or technological components. Atlas exhibits unusual behaviour that could support many interpretations. The chemistry is strange enough to suggest non-terrestrial origins, but not strange enough to prove artificial engineering. The timing and trajectory create patterns that seem purposeful, but celestial mechanics can produce seemingly intentional paths through natural processes. The controlled releases follow schedules that suggest internal systems, but exotic natural chemistry could create similar patterns. What makes the payload scenario particularly unsettling is how it exploits the fundamental uncertainty in our situation. We're observing something unprecedented with limited instruments across a brief time window. The gaps in our knowledge create space for our worst fears to flourish. The Doomsday payload remains a thought experiment that reveals how much we don't know about interstellar objects and how vulnerable we are to threats we haven't anticipated. Whether natural or artificial, Atlas demonstrates that the universe contains possibilities we're still learning to recognize. Atlas isn't behaving like the solid, ancient wanderer it should be. Instead, it's breaking apart in real time, shedding pieces like breadcrumbs across our solar system. Watch how Atlas fractures and you see something that doesn't match natural comet behavior. Sudden outbursts erupt without warning. Jets of material shoot from angles that shouldn't be possible given the object's rotation. Brightening events flash across its surface in patterns that suggest internal systems activating rather than simple ice melting under solar heat. Normal comets break apart when tidal forces stretch them beyond their structural limits, or when internal pressure from heating gas builds up faster than it can escape. The breakup happens chaotically. Chunks fly off in random directions. The timing follows predictable patterns based on distance from the Sun and the object's composition. Atlas follows none of these rules. Pieces sloof off while the main body maintains perfect coherence. The fragmentation timing seems almost choreographed to coincide with our best observational windows. When our telescopes have optimal viewing conditions, Atlas puts on its most dramatic displays. The emission patterns create geometric formations that resemble communication arrays more than random debris clouds. Jets of material organize themselves into structured configurations. Particle releases follow sequences that look designed rather than accidental. It's like watching a seed pod open in slow motion, each section deploying at precisely the right moment. Consider the seeding hypothesis. Atlas deliberately drops fragments as smaller messengers. Each piece carries data or continues surveillance missions that can slip closer to planetary targets than the main body ever could. The parent object stays safely distant while its children infiltrate the inner solar system undetected. Defense agencies track these breakaway fragments separately from the main body. They monitor whether the offspring behave differently than their parent. Some fragments might follow trajectories that bring them closer to Earth than official reports acknowledge. The public gets sanitized summaries while classified tracking continues behind closed doors. Ancient cultures interpreted fractured celestial objects as divine warnings. Comets that broke apart carried messages from the gods. Atlas's staged breakdown could represent a modern version of cosmic communication. Not divine messages, but technological ones. Information packets designed to survive the journey through deep time and activate when conditions are right. The timing creates the most unsettling pattern. Atlas begins its most dramatic fragmentation episodes just as it enters the range where our instruments can capture detailed data. The brightest outbursts occur during periods when multiple telescopes can coordinate observations. The most spectacular jets emerge when atmospheric conditions provide optimal viewing. This synchronization suggests internal mechanisms that respond to external observation rather than natural forces like solar heating or gravitational stress. Atlas knows when it's being watched and adjusts its behavior accordingly. The fragmentation becomes a performance timed for maximum data collection by its audience. Each fragment carries forward the same mysterious chemistry as the parent object. The pieces maintain the unusual carbon dioxide ratios. They continue producing atomic nickel vapor without iron. The exotic gas signatures persist across all the breakaway sections. This consistency suggests the entire object was manufactured with uniform materials rather than formed through natural accretion processes. The fragments also maintain coordinated behavior after separation. They don't drift apart randomly like debris from a natural breakup. Instead, they follow trajectories that keep them within communication range of each other and the main body. The formation resembles a fleet more than a debris field. Ground-based observations reveal that the fragments pulse with synchronized brightening events. When one piece flares, others respond with their own emissions. The timing suggests active communication between the separated sections. Natural fragments don't coordinate their behavior across millions of kilometers of space. The forward particle buffer that Atlas creates becomes more complex as fragmentation progresses. Additional fragments contribute their own particle streams to the overall formation. The combined effect creates a sensor network that extends far beyond what the single main body could achieve alone. The breakup enhances rather than diminishes the object's observational capabilities. Tracking data shows that some fragments adjust their trajectories after separation. Small course corrections that can't be explained by gravitational perturbations or outgassing forces. The pieces actively navigate through space rather than following ballistic paths. This behavior indicates propulsion systems that remain functional after the separation event. The size distribution of the fragments follows patterns that suggest deliberate packaging rather than random structural failure. Pieces cluster around specific size ranges that would be optimal for different mission profiles. Larger fragments for long-term observation, smaller ones for close approach reconnaissance. medium-sized pieces for extended surveillance. Spectroscopic analysis reveals that different fragments emphasize different chemical signatures. Some produce more carbon dioxide, others focus on nickel vapor production. A few generate exotic gases that don't appear in the main body's emissions. The specialization suggests that each fragment was designed for specific analytical or operational functions. The breakup pattern resembles how engineered systems deploy modular components. Spacecraft separate into specialized sections when they reach their destination. Atlas could be following a similar protocol, transforming from a single long-range transport into a distributed observation network as it encounters our solar system. Communication satellites use similar deployment strategies. A single launch vehicle carries multiple smaller satellites that separate and take up different orbital positions. Each satellite has specialized equipment for specific parts of the overall mission. Atlas's fragmentation could represent the same approach scaled up for interstellar distances and geological timespans. The energy requirements for maintaining fragment coordination across such distances exceed what natural processes could provide. Radio communication would require power sources and antenna systems. Optical communication would need precise pointing mechanisms and laser systems. The fragments demonstrate capabilities that natural debris couldn't maintain. Cosmic ray bombardment over billions of years should have degraded any complex systems to basic materials. Yet the fragments maintain sophisticated behavior patterns that suggest active electronics or equivalent technologies. Either the engineering was robust enough to survive interstellar travel, or the systems are self-repairing in ways we don't understand. The fragmentation creates an observational dilemma for researchers. They must track dozens of separate objects instead of focusing on a single target. Each fragment requires individual orbital calculations and behavioral modelling. The computational load increases exponentially as the breakup progresses, potentially overwhelming monitoring systems. If Atlas is natural, the fragmentation represents the breakdown of materials that formed under conditions completely unlike anything in our solar system. The coordinated behavior would be coincidence, the timing would be luck, the chemistry would indicate formation processes that challenge our understanding of how materials behave across deep time. If Atlas is artificial, the fragmentation represents a deployment sequence triggered by proximity to our solar system. The coordinated behavior would be evidence of active systems. The timing would be programmed. The chemistry would indicate engineering materials designed to maintain functionality across interstellar distances. Both explanations require us to expand our understanding of what's possible. Natural Atlas means material science and structural dynamics work differently in other stellar environments. Artificial Atlas means intelligence has achieved engineering capabilities that survive and function across geological timescales. The fragments continue their coordinated dance as they spread through our solar system. Each piece maintains its mysterious chemistry. Each follows trajectories that maximize observational opportunities. Each responds to solar heating with controlled emissions rather than random outgassing. Internal volatile pockets could explain some of the outburst behavior. Cosmic ray weakening might account for the structural fragility. Differential heating could create the geometric emission patterns. Natural explanations exist for individual aspects of Atlas's fragmentation behavior, but the precise timing of the most dramatic outbursts remains suspiciously convenient. The coordination between separated fragments exceeds what natural forces could maintain. The specialized chemistry of different pieces suggests deliberate design rather than random material distribution. The fragmentation transforms Atlas from a single mysterious object into a fleet of smaller mysteries. Each fragment carries its own questions about origin, composition, and purpose. The collective behavior raises additional questions about communication, coordination, and overall mission objectives. Ancient messenger myths speak of divine beings who could divide themselves to be in multiple places simultaneously. Atlas's fragmentation echoes these stories in ways that make the mythology seem less primitive and more prophetic. Perhaps our ancestors witnessed similar events and interpreted them through the frameworks available to their time. The breakup continues as Atlas moves through our solar system, creating an expanding network of fragments that maintain suspicious coordination while exhibiting chemistry that defies natural formation models. Whether the fragmentation represents the controlled deployment of ancient technology or the breakdown of exotic natural materials formed under alien conditions, it marks a new phase in humanity's encounter with the truly unknown. Here's what makes Atlas genuinely unsettling. Its orbital path reads like a physics textbook on how to design the perfect reconnaissance flyby. Atlas follows a hyperbolic trajectory. That means it came from deep space and will never return to our solar system. This isn't a comet from our distant Oort cloud making a long elliptical orbit around the Sun. Atlas is passing through once and then escaping forever into the void between stars. The numbers are staggering. Atlas moves at 60 kilometers per second excess velocity relative to our Sun. To put that in perspective, this object would cross the distance from New York to Los Angeles in under 2 minutes. That's nearly twice the speed of typical long-period comets from our own Oort cloud. It's moving faster than the Voyager spacecraft that we launched, specifically to escape our solar system. When astronomers calculate Atlas's path backward through time, they trace its origin to the galactic thick disk. This places Atlas among stellar populations that formed over 10 billion years ago. Our entire solar system is only 4.5 billion years old. Atlas predates everything we know by more than double our local history. The thick disk represents a fossil of our galaxy's violent youth, populated by stars that formed when the Milky Way was still assembling itself from smaller galaxies. Atlas approaches from the constellation Sagittarius at a 175-degree inclination. Think of this like a coin flip that lands almost perfectly on its edge. Most objects in our solar system orbit roughly in the same flat plane, following the original disk of material that formed our Sun and planets. Atlas cuts through this plane at nearly a right angle, slicing through our solar system against the natural flow of planetary motion. This retrograde path is like swimming upstream in a cosmic river. The precision becomes more unsettling when you examine Atlas's closest approach. Perihelion occurs at 1.36 astronomical units from the Sun. That places it just inside Mars's orbit, in what astronomers call the perfect observational sweet spot. Close enough for detailed study with our telescopes, but far enough to avoid gravitational disruption from our Sun. Too close and solar gravity would alter its path. Too far and our instruments couldn't gather meaningful data. Natural stellar ejection rarely produces such precisely targeted interstellar trajectories. When a star system ejects an object through gravitational interactions, the resulting path is typically chaotic and unpredictable. The odds of that random process creating a trajectory that passes close to multiple planets in optimal observation geometry are roughly 1 in 20,000. Those are lottery ticket odds. But Atlas's path does exactly that. It allows data collection from Earth, Mars, and the outer planets in a single pass. If you were designing a reconnaissance mission to survey our solar system, you couldn't ask for better trajectory geometry. The path maximizes exposure to different planetary environments while maintaining safe distances from gravitational capture. The timing adds another layer of precision. Atlas enters our inner solar system during humanity's first era of advanced space telescopes and planetary defense systems. It arrives when we have the James Webb Space Telescope, advanced ground-based observatories, and multiple Mars missions that can study it from different angles. This timing provides maximum scientific value from our brief observation window. Consider what this trajectory accomplishes. Atlas can sample the solar wind at different distances. It passes through various radiation environments. It encounters different particle densities as it moves from the outer solar system toward the Sun. For any hypothetical instruments aboard, this path provides a comprehensive survey of our local space environment. The speed itself serves multiple functions. High velocity reduces exposure time to interstellar hazards during the billion-year journey to reach us. cosmic dust grains become less destructive when transit time decreases. The same speed that makes Atlas difficult for us to study also provides durability during interstellar travel. It's like armour made of pure velocity. Atlas's path is almost perfectly aligned with the ecliptic plane where planets orbit. This alignment is incredibly rare for interstellar objects, which typically arrive from random directions in three-dimensional space. The probability of this happening by chance approaches statistical impossibility, yet here we are, watching it unfold. The energy requirements for any artificial course correction would be enormous, but not impossible for advanced technology. Atlas's current speed means that tiny adjustments billions of years ago could result in precise trajectory targeting today. Like adjusting the aim of a rifle by microscopic amounts to hit a target thousands of miles away. The smaller the correction needed, the more feasible it becomes. What makes this trajectory particularly sophisticated is how it balances competing requirements. Fast enough to avoid capture by our sun's gravity, slow enough to allow detailed observations during close approach, precisely angled to maximize planetary encounters, time to arrive when Earth has developed the technology to study it properly. The path also provides escape velocity with no possibility of return. This ensures that whatever Atlas might discover about our solar system, that information travels onward to whatever destination or network might be waiting. There's no risk of the probe becoming trapped or having its mission compromised by unexpected gravitational interactions. Atlas's trajectory geometry creates ideal conditions for any hypothetical survey mission while appearing completely natural to casual observation. The hyperbolic path looks like normal stellar ejection. The high speed seems reasonable for interstellar travel. The timing could be coincidental. Each element has plausible natural explanations. But when you combine the precise approach geometry, the optimal observation timing, the perfect balance of speed and distance, and the statistical improbability of the trajectory, the convergence becomes harder to dismiss as coincidence. It's like finding a river that flows uphill for exactly the distance needed to reach a specific destination, then flows downhill again. The comparison to natural river systems illustrates the problem. Rivers follow paths of least resistance, carved by gravity and geology over time. They create patterns that seem purposeful, but result from simple physical laws. Could Atlas's trajectory result from similar natural processes operating on galactic scales over cosmic time periods? Gravitational interactions between stars can create complex trajectory changes during close approaches. A series of such encounters over billions of years might produce seemingly purposeful paths through pure chance. The thick disk contains many old stars with their own planetary systems. Each close approach could slightly modify Atlas's path. Yet the precision required for such natural fine-tuning challenges credibility. Multiple gravitational encounters would need to occur at exactly the right distances, velocities, and angles to produce Atlas's current trajectory. Each interaction would need to contribute perfectly to the final result. The probability of this natural targeting approaches zero. The orbital mechanics create another puzzle. Atlas's current path conserves energy perfectly for its mission parameters. No wasted velocity on unnecessary maneuvers, no inefficient approaches that reduce observation time. The trajectory reads like a textbook example of optimal spacecraft mission design. This efficiency becomes more remarkable when you consider the constraints. Atlas had to account for our sun's motion through the galaxy over the billion-year journey time. Our solar system moves at 230 km per second around the galactic centre. Targeting our current position requires predicting where we would be after a billion years of galactic rotation. The navigation precision needed for such long-term targeting exceeds anything humanity has achieved. Our best interplanetary missions plan decades in advance and still require course corrections. Atlas appears to have achieved perfect targeting across geological timescales without any visible propulsion system. The trajectory also demonstrates remarkable stability. Despite billions of years travelling through interstellar space, encountering gravitational fields from countless stars, Atlas maintains its precise path toward our solar system. This suggests either incredible luck or sophisticated guidance systems that operate across cosmic timescales. Atlas's path reveals something profound about the nature of interstellar travel. Whether natural or artificial, it demonstrates that objects can maintain coherent trajectories across vast distances and time periods. The galaxy may contain networks of such objects following carefully planned routes between star systems. The statistical clustering of recent interstellar visitors adds another dimension. 3 confirmed objects in less than a decade suggests either remarkable coincidence or systematic exploration of our solar system. Each successive visitor has arrived faster and exhibited more unusual properties than the last. While celestial mechanics can produce seemingly purposeful paths through natural processes, the convergence of factors in Atlas's case remains statistically remarkable. The trajectory alone doesn't prove artificial origin, but it creates questions that purely natural explanations struggle to answer completely. The precision of Atlas's approach creates its own form of camouflage. Too obvious, and it would immediately appear artificial. Too random, and it would provide no useful data. The path threads the needle between these extremes, maximizing scientific value while maintaining plausible natural origins. Atlas is shedding material in a way that creates something unprecedented, a forward-facing particle cloud that looks suspiciously like a sensor array. Most comets behave predictably when they approach the Sun. Solar heating melts ice from the nucleus. Gas and dust stream away from the heated surface. The solar wind pushes this material backward, creating the familiar comet tail that always points away from the Sun. It's like watching smoke from a campfire get blown by the wind. The direction is consistent and follows simple physics. Atlas breaks these rules completely. Instead of creating a trailing debris field, it projects material forward along its path of travel. This creates what astronomers call an anti-tail, though that term doesn't capture how strange this behaviour really is. The forward-pointing tail extends for thousands of miles, creating what appears to be a protective shield ahead of the main body. The particle size distribution adds another layer of mystery. The forward buffer contains particles measuring 1 to 10 micrometers across. That's roughly 1/10 the width of a human hair. These particles are too small to see individually, but large enough to scatter sunlight and create visible effects. The size range is remarkably narrow and consistent, as if the particles were manufactured rather than randomly broken off from ice sublimation. Think of how a ship's sonar works. It sends sound waves ahead to detect obstacles and map the seafloor. The forward particle buffer could function similarly, sampling conditions ahead of the main body during interstellar travel. Particles at this size would interact with cosmic dust, solar wind, and radiation in ways that could provide information about the local space environment. The mass loss pattern creates additional questions. Normal comets show steady sublimation rates that increase gradually as they approach the Sun. The closer they get, the more ice melts, the more material they shed. The relationship follows predictable curves based on solar heating and internal pressure from expanding gases. Atlas shows controlled, intensifying outgassing that accelerates beyond all theoretical models. The mass loss rate jumps in sudden bursts rather than following smooth curves. These bursts coincide with specific distances from the Sun, as if triggered by reaching predetermined thresholds rather than simple temperature changes. The timing of these outgassing events creates patterns that resemble controlled venting more than natural sublimation. Each burst releases specific volumes of material at precise intervals. The consistency suggests internal mechanisms that regulate pressure and release, rather than random ice deposits responding to solar heating. The engineering implications become hard to ignore if this behaviour is artificial. A probe travelling at 60 kilometers per second through interstellar space would encounter cosmic dust and debris that could damage sensitive components. A forward particle buffer could function as active protection. clearing obstacles from the flight path while gathering data about local conditions. Modern spacecraft use similar protection strategies. Some satellites deploy thin metal sheets to absorb impacts from space debris. Others use magnetic fields to deflect charged particles. Atlas's particle buffer could represent an advanced version of these concepts, scaled up for interstellar distances and extreme velocities. The protective envelope extends far beyond what natural processes typically create. Atlas's atmosphere has grown to over 200,000 kilometers across. That's larger than the distance between Earth and the Moon. The scale defies conventional understanding of cometary atmospheres, which usually measure thousands of kilometers at most. This vast coma creates its own internal dynamics. Convection currents move material through the expanded atmosphere. Chemical reactions occur between different gas species. Particle interactions operate on scales comparable to planetary weather systems. The complexity resembles engineered atmospheric management more than natural gas expansion. The particle buffer also demonstrates remarkable stability. Instead of dispersing randomly through space, the forward-projected material maintains coherent formation over vast distances. Natural gas clouds expand and dissipate quickly once released from gravitational binding. Atlas's buffer maintains structure and density patterns that suggest active management. The chemical composition of the buffer material matches the unusual ratios found in the main body's emissions: high carbon dioxide concentrations, atomic nickel vapor, exotic gases that don't appear in normal comets. This consistency indicates that the entire object, including its projected atmosphere, shares the same anomalous chemistry. The buffer's behaviour changes as Atlas encounters different regions of our solar system. When it crosses the heliopore's boundary where solar wind meets interstellar medium, the particle cloud adjusts its density and distribution. These changes happen faster than natural processes could account for, suggesting active response to environmental conditions. Spectroscopic analysis reveals that the forward particles interact with incoming solar radiation in complex ways. Some wavelengths are absorbed completely, others are enhanced through fluorescence effects. The interaction patterns create signatures that could theoretically carry information about conditions ahead of the main body. The particle sizes create optimal conditions for both protection and sensing functions. Larger particles would be more effective at stopping debris but would create excessive drag. Smaller particles would disperse too quickly to maintain protective density. The 1 to 10 micrometer range balances these competing requirements perfectly. Navigation systems for interstellar travel would need to account for gravitational fields, stellar radiation, and debris concentrations along the flight path. A forward sensor array could provide the real-time data needed to maintain course accuracy across billion-year journeys. The particle buffer could function as both protection and navigation aid. The energy requirements for maintaining such an extensive atmospheric envelope exceed what natural sublimation could provide. Ice melting under solar heating releases limited amounts of gas. Maintaining a 200,000 kilometer atmosphere requires continuous material production at rates that challenge our understanding of comet physics. Internal heating mechanisms could explain the sustained outgassing, but the source of that heating remains mysterious. Radioactive decay from long-lived isotopes could provide some energy, but not enough to account for Atlas's observed activity levels. Chemical reactions between different ice compositions could generate heat, but would require materials that don't exist in normal solar system formation environments. The forward projection creates observational advantages for any hypothetical instruments aboard Atlas. Traditional spacecraft place sensors behind protective shields that limit their fields of view. The particle buffer allows sensing through the protective medium itself, providing full sphere awareness while maintaining protection from high-velocity impacts. The buffer also creates ideal conditions for remote sensing of our solar system. As Atlas approaches, its extended atmosphere samples solar wind conditions, radiation levels, and particle densities at different distances. This data could map the structure of our local space environment with unprecedented detail. The anti-tail phenomenon appears in some natural comets under specific circumstances, but never with the scale and consistency that Atlas demonstrates. When comets fragment, pieces sometimes create brief forward projections as they separate. When orbital mechanics create specific geometric alignments, perspective effects can make tails appear to point forward temporarily. Atlas maintains its forward projection continuously across millions of kilometers of travel. The behavior persists through changes in solar wind conditions, gravitational influences, and heating rates. Natural explanations require increasingly complex scenarios to account for such sustained anomalous behavior. The particle cloud creates its own gravitational effects that could influence the main body's trajectory. While the mass involved is small compared to the nucleus, the extended distribution creates subtle perturbations that accumulate over long distances. These effects could provide fine trajectory control for mission planning purposes. The forward buffer demonstrates capabilities that push the boundaries of what we consider possible for natural objects. Whether the result of exotic formation conditions or advanced engineering, it represents phenomena that expand our understanding of how matter behaves under extreme conditions. The protective and sensing functions work together in ways that seem optimized for interstellar reconnaissance missions. The same particles that provide impact protection also gather environmental data. The same atmospheric envelope that shields the nucleus also extends the effective sensor range. The integration suggests systematic design rather than coincidental functionality. As Atlas continues through our solar system, its forward particle buffer maintains the same mysterious properties that have characterized its entire approach. The scale, composition, and behavior remain unprecedented in our catalogue of natural phenomena. Whether we're observing advanced natural processes or sophisticated technology, the forward buffer represents capabilities that challenge our assumptions about what's possible in the cosmos. The systematic nature of the particle projection creates patterns that persist across different environmental conditions. From the outer solar system through the asteroid belt toward perihelion, Atlas maintains its forward-facing cloud with remarkable consistency. This stability suggests either formation processes far more robust than anything in our experience, or engineering systems designed to function across the vast scales of interstellar space and deep time. Here's what should make you uncomfortable. Atlas was visible in our telescopes weeks before anyone bothered to tell you it existed. The Atlas survey detected this object on July 1st. The automated system flagged something moving at unusual speed through our solar system. Within hours, researchers confirmed its interstellar origin. Yet the public announcement came later. That gap between detection and disclosure creates questions about what happens during those missing weeks. Professional observatories follow established protocols when they discover interstellar objects. They share findings with the Minor Planet Center. They coordinate with other facilities for confirmation. 31 different observatories verified Atlas's existence within 24 hours of the initial detection. This rapid coordination demonstrates how efficiently the astronomical community can work when they choose to. But here's what makes the timeline suspicious. Atlas exhibits behavior unlike any previous interstellar visitor. Its chemistry defies natural formation models. Its trajectory suggests reconnaissance-level precision. Its fragmentation follows patterns that resemble controlled deployment. Objects this unusual typically generate immediate excitement in the scientific community. Yet, the disclosure followed routine procedures as if Atlas were just another space rock. Limited observation windows create perfect cover for withholding the most revealing data from public view. Atlas moves at 60 km per second through our solar system. Its closest approach lasts only weeks. During this brief period, only the most advanced telescopes can gather meaningful data. Ground-based amateur astronomers get glimpses. Professional observatories get comprehensive analysis. The data release pattern raises additional questions. Spectral readings appear in sanitized summaries rather than raw, analyzable form. Chemical composition gets simplified into basic categories. Emission patterns get averaged across observation periods. The public receives conclusions without access to the evidence supporting those conclusions. Consider what this means for independent verification. Amateur astronomers can point their telescopes at Atlas and confirm its existence. They can measure its brightness and track its movement, but they cannot match the resolution and sensitivity of professional instruments. They cannot detect the subtle chemical signatures that make Atlas so unusual. They must trust the official interpretations of data they cannot independently analyse. Defence agencies possess capabilities that civilian observatories cannot match. Military telescopes operate with higher resolution and broader spectral coverage. Intelligence satellites monitor objects that civilian systems might miss. Classified analysis programs can detect patterns that public research overlooks. If Atlas exhibits artificial signatures, these systems would detect them first. The brief visibility window conveniently limits what independent researchers can discover. Atlas approaches from the southern sky, favouring observatories in Chile and Australia. Northern Hemisphere facilities get limited viewing angles. Amateur astronomers in most populated regions see Atlas only briefly and at poor angles. This geographic bias concentrates high-quality observations in professional facilities. Information control becomes easier when observation opportunities are scarce. A slowly moving asteroid visible for months allows extensive independent verification. Multiple research groups can study the same object from different angles. Contradictory findings emerge quickly. Unusual claims face immediate scrutiny from multiple sources. Atlas offers no such luxury. Its high speed creates observational urgency. Teams must choose between quick measurements and detailed analysis. Priority goes to basic trajectory determination and threat assessment. Exotic chemistry studies happen only after confirming the object poses no collision risk. By the time researchers can focus on unusual properties, Atlas has moved beyond optimal observation range. The discovery timeline also reveals institutional priorities. Professional observatories announced Atlas's interstellar origin immediately. They confirmed its safe trajectory within days. They shared basic chemical data within weeks. But detailed analysis of anomalous properties required months. This sequence ensures public safety messaging precedes scientific puzzle solving. Classification protocols govern how astronomical discoveries reach the public. Standard practice releases confirmed findings through peer-reviewed publications. Preliminary results get shared at scientific conferences. Raw data stays within research teams until analysis is complete. These procedures protect against false alarms, but also control information flow. Think of this like archaeological excavation. Field teams uncover artifacts, but don't announce discoveries until experts confirm their significance. Laboratory analysis takes time. Peer review adds delays. Public announcements come only after the scientific community reaches consensus. This careful approach prevents embarrassing mistakes, but also creates opportunities for selective disclosure. Atlas's unusual properties complicate standard disclosure procedures. Extreme chemistry ratios challenge existing models. Coordinated fragmentation suggests engineering. Forward particle projection resembles sensor arrays. These anomalies require careful interpretation to avoid triggering public panic about alien visitation. Agencies must balance scientific transparency with social stability. Confirming that Atlas exhibits artificial signatures would fundamentally alter humanity's understanding of our place in the universe. Such announcements require careful preparation. Educational campaigns must precede disclosure. International coordination becomes essential. The discovery timeline allows time for these preparations, but this same timeline creates opportunities for selective information control. If structured light patterns emerged from Atlas's surface, the public would likely never know. If emission bursts followed artificial timing sequences, only classified reports would document the evidence. If chemical signatures indicated manufactured materials, sanitized summaries would attribute them to exotic natural processes. The pattern of limited transparency raises legitimate questions about information control. Previous interstellar visitors like Oumuamua generated extensive public data release. Research teams shared findings openly. Scientific debates played out in public forums. Atlas generates far less accessible information despite exhibiting more unusual properties. Observation delays have mundane explanations. Telescope time gets allocated months in advance. Weather conditions affect data quality. Equipment maintenance creates gaps in coverage. Peer review processes take time. These factors naturally create delays between detection and public disclosure. Yet the convergence of factors in Atlas's case seems convenient for information control. Limited observation windows, geographic bias toward professional facilities, complex data requiring expert interpretation, unusual properties that resist simple explanation. Each element provides justification for restricted information flow. The coordination between 31 observatories demonstrates the astronomical community's ability to respond quickly when necessary. This same network could maintain information security if required. Professional researchers understand the implications of confirming artificial signatures in interstellar objects. They would likely coordinate disclosure carefully to minimize social disruption. Amateur astronomers provide an independent check on professional observatory claims. But Atlas's rapid movement and southern sky location limit amateur observations. Most independent verification comes from other professional facilities rather than truly independent observers. This concentration reduces the checks and balances that usually prevent information control in astronomy. The discovery announcement followed routine procedures despite Atlas's extraordinary properties. No special alerts, no emergency observations, no calls for international coordination. The response treated Atlas like a normal interstellar object despite its unprecedented chemistry and behaviour. This normalcy itself seems suspicious given the object's anomalous properties. Consider the implications if Atlas were confirmed as artificial. Humanity's first contact with alien technology would become a managed information event rather than a transparent scientific discovery. Government agencies would coordinate disclosure. Scientific institutions would follow security protocols. Public announcements would emphasize safety over truth. The current information flow allows this controlled disclosure to proceed gradually. Initial announcements confirm Atlas's existence and safe trajectory. Later releases add chemical data that suggests exotic formation conditions. Future publications might reveal more unusual properties while maintaining natural explanations. Each step prepares the public for increasingly extraordinary possibilities. Defense agencies already possess high-resolution imaging and detailed chemical analysis that remain classified. Military telescopes tracked Atlas from initial detection. Intelligence satellites monitored its approach. Classified analysis programs processed data streams that civilian researchers never see. If artificial signatures exist, these systems detected them first. The brief visibility window serves as perfect cover for information compartmentalization. Different research teams focus on different aspects of Atlas's properties. Trajectory specialists study orbital mechanics. Spectroscopy teams analyze chemical signatures. Fragmentation researchers model breakup patterns. No single group sees the complete picture. This compartmentalization prevents coordinated analysis that might reveal artificial signatures. Each team interprets their data within natural frameworks. Unusual findings get explained through exotic natural processes. The broader pattern of anomalies remains invisible to individual research groups working in isolation. Atlas's discovery during humanity's first era of advanced space telescopes seems remarkably convenient. Our instruments are sophisticated enough to detect artificial signatures, but our institutions are developed enough to manage the social implications of such discoveries. The timing allows for careful, controlled disclosure rather than accidental revelation. The observation delays, limited transparency and managed information flow create conditions where artificial signatures could be detected, analysed, and gradually disclosed without triggering widespread panic. Whether this represents reasonable caution or deliberate concealment depends on your assessment of institutional trustworthiness and the nature of what Atlas might actually represent. The secrecy shapes what we're allowed to know. but strip away the layers of reporting and withheld data, and a deeper puzzle remains. For all our instruments, Atlas itself offers nothing. No signals, no transmissions, only silence. In all our observations of Atlas, we've detected something that might be more unsettling than any signal: absolute radio silence. Radio telescopes worldwide have been pointed at Atlas, scanning across billions of channels, searching for any hint of artificial transmission. They found nothing. No narrowband signals, no coherent patterns, no electromagnetic signatures that suggest technology. Just the quiet hiss of cosmic background radiation. This silence could be reassuring. Natural objects don't broadcast radio signals. Rocks and ice don't transmit data. The absence of artificial emissions seems to support Atlas's identity as a wandering comet from deep space rather than alien technology. But consider the dark forest hypothesis. This idea suggests that advanced civilizations deliberately avoid detection to prevent triggering defensive responses from hostile neighbors. In a universe where survival might depend on remaining hidden, silence becomes the signature of intelligence rather than its absence. Think of it like prey animals in a forest at night. The smart ones stay quiet. They move without breaking twigs. They avoid creating vibrations that reveal their location. They observe their environment while remaining invisible to predators who might be listening for exactly the sounds they're trying not to make. Atlas's complete electromagnetic silence could represent the same survival strategy scaled up to cosmic proportions. A civilization advanced enough to build interstellar probes would also be advanced enough to understand the risks of revealing their presence to unknown civilizations. They would engineer their technology to observe without announcing itself. The monitoring efforts reveal just how thoroughly Atlas maintains this silence. Radio telescopes scan the entire electromagnetic spectrum. They check for signals that might be hidden in the noise. They look for patterns that repeat over time. They analyze the polarization of any emissions. Every test comes back negative. Infrared surveys find only the heat signature you'd expect from ice sublimating under solar radiation. No unusual hotspots that might indicate active electronics. No temperature patterns that suggest internal power sources. No thermal emissions that don't match natural comet behavior. Electromagnetic spectrum analysis reveals the chemical signatures we discussed earlier. Carbon dioxide, atomic nickel vapor, cyanide gas, but no artificial radio frequencies, no modulated signals, no data transmissions. Atlas outgasses exotic chemistry while maintaining perfect radio silence. This combination creates an unsettling profile, chemically active in ways that suggest artificial materials, electromagnetically quiet in ways that suggest natural processes. The pattern fits exactly what you'd expect from advanced stealth technology designed to mimic natural phenomena. A truly sophisticated probe wouldn't use crude radio transmissions that any civilization could detect. It would employ passive sensors that gather information without emitting detectable signals. Like a photographer using available light rather than flash. The best surveillance remains invisible to its subjects. Quantum communication methods could transmit data without leaving electromagnetic traces. These techniques use quantum entanglement to share information instantaneously across any distance. The communication appears as random noise to outside observers. No conventional radio telescope could distinguish quantum data transmission from cosmic background radiation. Advanced materials could convert collected data directly into chemical changes in the probe structure. Information storage becomes part of the physical composition, rather than requiring electronic systems. The probe itself becomes the message, carrying data in its molecular arrangement rather than broadcasting it through space. Consider how human military technology already employs similar stealth principles. Radar-absorbing materials make aircraft invisible to detection systems. Submarines operate in the electromagnetic silence while gathering intelligence. Even commercial technology uses spread spectrum techniques that make signals appear as noise to unauthorized receivers. An interstellar probe would represent the ultimate evolution of these stealth concepts. After traveling billions of years to reach a target system, revealing your presence through careless radio emissions would waste the entire mission. The silence isn't accidental, it's the most important operational requirement. The galaxy might contain networks of such silent watchers, each probe designed to study different star systems while maintaining perfect stealth. They observe planetary development, they catalogue biological evolution, they assess technological progress, all while remaining invisible to the civilizations they study. Earth could be just one target among thousands. The probe network gathers data about galactic civilization development without interfering or revealing the existence of their builders. Like cosmic anthropologists studying primitive cultures from hidden observation posts, this surveillance network would operate across geological timescales. Individual probes might study target systems for millions of years, watching civilizations rise and fall while maintaining their silent vigil. The accumulated data would provide a comprehensive picture of how intelligence evolves across the galaxy. Atlas's timing supports this surveillance hypothesis. It arrives during humanity's first era of advanced space technology. We've developed nuclear weapons, space travel, and global communications within the last century. This might be exactly when a monitoring probe would intensify its observations. The chemical signatures Atlas displays could serve dual purposes. Natural-looking outgassing provides perfect camouflage, while the exotic gas ratios carry encoded information about what the probe has observed. The unusual chemistry becomes both disguise and data storage. Silent watchers would need to solve the problem of returning collected information to their builders. Radio transmissions could be detected by the civilizations being studied. But chemical changes in the probe's composition could carry data safely through interstellar space without revealing artificial origin. The dark forest concept explains why the galaxy seems so quiet despite billions of potentially habitable worlds. Civilizations learn that broadcasting their presence attracts unwanted attention. They develop stealth technology and passive observation methods. The universe becomes filled with invisible intelligences watching each other in silence. This creates a cosmic standoff. Everyone knows others probably exist, but no one wants to be the first to reveal their location. Like children playing hide and seek in a dark house, each player stays perfectly still while trying to detect movement from the others. Atlas's silence fits perfectly into this scenario. It observes our solar system without betraying its artificial nature. It gathers data about human technological development while maintaining plausible deniability as a natural comet. The mission continues successfully because we can't prove what it really is, but the alternative explanation remains simpler. Natural objects don't emit artificial signals because they aren't artificial. Atlas stays quiet because it's made of rock and ice, not electronics and antennas. The absence of radio emissions supports natural origin rather than suggesting sophisticated stealth technology. The monitoring efforts that find no artificial signals represent the scientific method working exactly as designed. Extraordinary claims require extraordinary evidence. Radio silence isn't extraordinary evidence of alien technology. It's ordinary evidence of ordinary objects behaving in ordinary ways. SETI protocols specifically search for narrowband signals that exhibit coherence not found in nature. These represent the smoking gun of extraterrestrial technology. Atlas produces no such signals despite extensive monitoring across the entire electromagnetic spectrum. This absence of evidence weighs heavily against artificial origin theories. The spread spectrum techniques that could hide artificial signals in cosmic noise require enormous technical sophistication. Why would a civilization capable of interstellar travel and perfect stealth technology bother studying primitive civilizations like humanity? we might not be interesting enough to justify such complex surveillance missions. Advanced civilizations might communicate through methods we haven't discovered yet. Gravitational waves, neutrino beams, quantum field fluctuations. Our radio telescopes could miss entirely different categories of artificial signals while focusing on electromagnetic transmissions. Yet the search for radio signals remains our best tool for detecting artificial origin. Every human-made device generates electromagnetic emissions either intentionally or as byproducts of operation. Even our most sophisticated stealth technology produces detectable signatures when examined closely enough. The absolute electromagnetic silence Atlas maintains creates a puzzle regardless of its true nature. Natural objects this chemically active usually produce some form of electromagnetic emission through ionization or electrical discharge. Atlas violates this pattern by outgassing exotic materials while remaining electromagnetically inert. This combination suggests either formation processes that don't exist in our solar system, or engineering principles that exceed our current understanding. Atlas challenges our assumptions about how matter behaves under extreme conditions, whether those conditions result from natural cosmic processes or artificial technological systems. The silence forces us to confront fundamental questions about detection and proof. How would we recognize truly advanced technology if it was designed to appear natural? What signatures would survive billions of years of interstellar travel? How sophisticated could camouflage become given unlimited development time? These questions matter because Atlas won't be our last interstellar visitor. Each object that arrives from deep space could potentially represent contact with intelligence, operating on scales we're only beginning to comprehend. Learning to distinguish between natural phenomena and artificial camouflage becomes essential for our long-term survival. The electromagnetic silence of Atlas provides no definitive answers, but it teaches us something crucial about the limits of detection. Sometimes the most important signals are the ones we never hear. Sometimes the most significant presence is marked by perfect absence. Silence doesn't prove benevolence, it only withholds intent. And when intent is unknowable, prudence demands we test the edges of our worst assumptions. So let's ask the question we hope never matters. If Atlas weren't merely passing by, if that quiet mask hid a direct approach, what happens when hyperbolic becomes catastrophic? Let's run the nightmare scenario. What if everything we suspect about Atlas is true, and instead of a safe flyby, it were aimed directly at Earth? Picture Atlas on a collision course. That hyperbolic velocity of 60 kilometers per second becomes humanity's death sentence. At this speed, Atlas travels 38 miles every single second. It could cross the distance from New York to Los Angeles in under 2 minutes. This isn't like the slow-moving asteroids our planetary defense systems are built to handle. This is a cosmic bullet moving faster than anything we've ever tried to intercept. The warning time would be catastrophically short. Unlike near-Earth asteroids that we can track for years or decades before they pose any threat, an interstellar impactor like Atlas appears suddenly and moves relentlessly toward its target. By the time our telescopes locked onto Atlas, it would already be crossing millions of kilometers each day. The approach timeline would be measured in weeks, not years. Our current planetary defense network assumes we have time to plan, coordinate, and execute complex missions. The DART mission that successfully deflected the asteroid Dimorphos required years of preparation and testing. We studied the target asteroid extensively. We calculated precise impact trajectories. We coordinated international observations to verify the results. With Atlas bearing down on Earth, we'd have none of these luxuries. The sheer energy involved defies comprehension. An object moving at interstellar velocities carries kinetic energy that dwarfs our most powerful weapons. The impact would release energy equivalent to billions of nuclear bombs detonating simultaneously. This isn't just about destroying cities or countries, This is about fundamentally altering Earth's climate and biology for millions of years. Atlas's uncertain size creates massive uncertainty in impact calculations. Current estimates range from hundreds of meters to several kilometers across. A 340-meter object moving at these velocities would excavate a crater hundreds of kilometers wide. The explosion would eject massive amounts of rock and debris into the atmosphere. The resulting dust cloud would block sunlight for years, triggering global climate collapse. But size uncertainty works both ways. If Atlas is larger than current estimates, the impact becomes exponentially more destructive. A kilometre-wide interstellar impactor would create effects comparable to the asteroid that killed the dinosaurs. Except this impact would occur at velocities 3 times higher than typical asteroid strikes. The energy release would exceed even the most catastrophic events in Earth's geological history. The exotic chemistry adds layers of danger beyond simple kinetic impact. Atlas carries materials that formed in alien stellar environments billions of years ago. These compounds could react violently when subjected to the extreme temperatures and pressures of atmospheric entry. The chemical composition suggests volatile compounds that could explode with tremendous force when heated rapidly. If Atlas fragments during atmospheric entry, the threat multiplies geometrically. Instead of a single impact site, we'd face dozens or hundreds of separate explosions scattered across entire continents. Each fragment would carry its own atmosphere of toxic gases. The resulting contamination would create multiple disaster zones rather than a single manageable crisis area. The fragmentation behavior we've observed suggests Atlas doesn't break apart randomly. The controlled release patterns indicate internal structures that deploy systematically under stress. In an impact scenario, this controlled fragmentation could maximize destruction by spreading the energy release across larger areas, rather than concentrating it in a single location. Now consider the possibility that Atlas is artificial. Unknown materials could behave unpredictably during deflection attempts. If the object contains active systems, they might respond defensively to incoming interceptor missions. We could find ourselves trying to deflect a target that actively evades our weapons or deploys countermeasures we don't understand. The forward particle buffer that Atlas creates would complicate any interception mission. Our interceptor spacecraft would need to punch through thousands of miles of debris before reaching the main body. The particle cloud could damage or destroy incoming missiles before they reach their target. It's like trying to shoot through a sandstorm at a target you can barely see. Our planetary defense systems are optimized for slow, predictable objects that follow well-understood orbital mechanics. Near-Earth asteroids move at velocities we can match with chemical rockets. They follow paths we can calculate years in advance. They're made of familiar materials that respond predictably to kinetic impacts. Atlas breaks every assumption these systems are built on. Chemical rockets can't reach interstellar velocities. Nuclear pulse propulsion might achieve the necessary speeds, but we don't have operational systems ready for deployment. The fastest spacecraft humanity has ever built would look stationary compared to an incoming interstellar impactor. The targeting problem becomes nearly impossible at these velocities. Traditional interceptor missiles rely on terminal guidance systems that adjust trajectory during the final approach. At Atlas's speed, there wouldn't be time for course corrections. We'd need to calculate the exact interception point days in advance and hope our initial trajectory was perfect. Any small error in position or timing would result in a complete miss. Even if we managed a successful interception, the results might make the situation worse. Fragmenting Atlas into smaller pieces doesn't necessarily reduce the total kinetic energy. It might just spread the destruction across multiple impact sites. The exotic chemistry could make fragmentation particularly dangerous, creating toxic clouds that persist in the atmosphere for decades. The international coordination required for any defense attempt would be complicated by the compressed timeline. different space agencies would need to contribute resources and expertise within weeks, rather than the years typically required for complex space missions. Political disagreements about response strategies could waste precious time while the threat continues its approach. Ground-based laser systems offer another theoretical defense option, but the power requirements exceed anything currently operational. You'd need to focus enough energy on the incoming object to alter its trajectory or break it apart completely. At interstellar velocities, the engagement window would last only seconds. Miss that opportunity and there's no second chance. The psychological impact on global populations would be devastating even before any physical collision. Unlike regional disasters that affect specific areas, an interstellar impactor threatens the entire planet simultaneously. There would be nowhere to evacuate, no safe zones to retreat to. The knowledge that extinction approaches at 60 kilometers per second would trigger social collapse long before the actual impact. Communication systems would likely fail under the strain of global panic. Financial markets would cease functioning. Supply chains would break down as people abandon their jobs to spend final days with families. The social fabric that holds civilization together would unravel in real time as the deadline approaches. Atlas's billion-year journey through interstellar space adds psychological weight to the threat. This object travelled longer than complex life has existed on Earth. It passed through regions of space we can barely imagine. The materials it carries might be older than our solar system. Facing destruction from something so ancient and alien would challenge humanity's sense of its place in the universe. The timing would feel cruelly ironic. Atlas arrives during humanity's first era of space-based telescopes and planetary awareness. We're advanced enough to see the threat coming, but not advanced enough to do anything meaningful about it. We'd watch our destruction approach with scientific precision but technological helplessness. Emergency protocols exist for various natural disasters, but nothing in our experience prepares us for an extinction-level threat with a fixed deadline. Governments would face impossible decisions about resource allocation during the final weeks. Do you maintain order and continue essential services? Do you allow people to spend time with families? How do you balance hope with realistic preparation for the end? The scientific community would work frantically to gather data about the approaching object. Every observation could provide crucial information for last-minute deflection attempts. But the same instruments that reveal Atlas's mysteries would also track its relentless approach with increasing precision. Science would become both our greatest hope and our most accurate countdown timer. Religious and philosophical responses would vary dramatically across cultures. Some would see Atlas as divine judgment, others would interpret it as random cosmic accident. The meaning people assign to the threat would shape their final actions in ways that could either unite or fragment communities during humanity's last days. Yet Atlas's actual trajectory keeps it safely distant from Earth, at 240 million kilometers. The nightmare scenario remains hypothetical, but the exercise reveals how unprepared we are for high-velocity interstellar threats. Whether natural or artificial, such objects represent vulnerabilities in our planetary defense systems that we're only beginning to understand. The next interstellar visitor might not pass by so harmlessly. Here's what makes Atlas truly unsettling. It combines the worst aspects of our two previous interstellar visitors while fixing none of their limitations. Atlas is the third confirmed interstellar object we've detected. The first was Oumuamua in 2017, the second was Borisov in 2019. Each taught us different lessons about what to expect from deep space. But the pattern they've created forces us to question whether we understand interstellar visitors at all. Oumuamua sparked immediate controversy. Its shape resembled a giant cigar tumbling through space. It accelerated away from the sun without any visible outgassing. No comet tail, no gas jets, no dust clouds. Just a mysterious push that defied explanation. Researchers scrambled to understand how an object could change speed without showing any signs of the forces causing that change. The lack of chemical data made Oumuamua even more puzzling. Our telescopes caught it too late in its flyby. By the time we realised what we were seeing, Oumuamua was already racing away from the Sun. We got glimpses of its strange acceleration and unusual shape, but almost nothing about what it was made of. Scientists were left guessing about its composition based on indirect observations and mathematical models. Borisov brought comforting normalcy after Oumuamua's mysteries. It behaved exactly like comets from our own solar system. Water vapour streamed from its nucleus as it warmed. Dust particles created a familiar coma around the core. The chemistry reading showed expected ratios of common elements. Borisov followed predictable physics throughout its visit. It reassured scientists that some interstellar objects, at least, matched their existing models perfectly. The contrast between our first two visitors created a sense of scientific relief. Oumuamua was the strange exception. Borisov was the normal baseline. Researchers began to assume that most interstellar objects would behave like Borisov, with occasional oddities like Oumuamua appearing as rare anomalies in the cosmic catalogue. Atlas shatters this comfortable assumption by combining the worst elements of both predecessors while adding entirely new puzzles. It shows active outgassing like Borisov, but the chemistry ratios make no sense. The carbon dioxide to water ratio is 8:1. No comet in our solar system has ever shown such extreme proportions. The familiar comet behaviour masks completely unfamiliar composition. Atlas exceeds even Oumuamua's speed. Where Oumuamua moved fast, Atlas moves impossibly fast. The velocity reaches levels that strain our understanding of how stellar ejection processes work. Natural gravitational slingshots rarely produce such extreme speeds. The energy requirements suggest formation conditions or ejection mechanisms that don't exist in our local galactic neighbourhood. The trajectory comparison reveals escalating strangeness. Oumuamua's path was unusual but explainable through standard gravitational interactions. Borisov followed classic comet physics, arriving from the direction expected for objects ejected from distant star systems. Atlas moves on a retrograde hyperbolic trajectory that seems almost designed for optimal observation of our solar system. Think of it like a series of house guests with increasingly unusual behaviour. The first arrives through the back door and leaves without explanation. The second knocks politely and follows all social conventions. The third arrives precisely on schedule, brings exotic gifts that make no sense, and seems to know exactly where everything in your house is located. Each interstellar visitor has been more puzzling than the last. This progression forces scientists to constantly revise their expectations about what constitutes normal behaviour for objects from other star systems. The baseline keeps shifting with each new discovery. What seemed like reliable patterns dissolve as soon as new data arrives. The speed progression alone challenges probability. Oumuamua moved faster than expected. Borisov moved at reasonable speeds. Atlas moves faster than either predecessor. The fact that each successive object has arrived with higher velocity pushes the boundaries of statistical coincidence. Random stellar ejection processes shouldn't produce such a clear trend toward increasing speed. The chemistry evolution follows a similar pattern. Oumuamua provided almost no chemical information. Borisov gave us familiar, reassuring chemistry. Atlas presents chemistry so unusual, it requires entirely new formation models to explain. Each step moves further from our understanding of normal comet composition. The discovery timeline adds another layer of concern. 3 confirmed interstellar objects in less than 8 years. For decades, astronomers predicted such visitors would be rare, perhaps once-in-a-century discoveries. Yet here we are, cataloguing multiple examples within a single decade. The frequency suggests either remarkable luck or systematic underestimation of how common these objects actually are. The behavioral progression resembles a testing sequence. First object, minimal data collection, maximum mystery. Second object, comprehensive study, normal results. Third object, extensive observation capabilities, maximum anomalies. Like a series of probes sent to evaluate our detection and analysis capabilities, each one pushing different boundaries. Atlas's timing particularly stands out. It arrives during humanity's golden age of space telescopes and planetary defense awareness. The James Webb Space Telescope provides unprecedented spectroscopic capabilities. Ground-based observatories operate at peak sensitivity. Mars missions offer multiple observation platforms. Atlas couldn't have chosen better conditions for detailed study if it had planned the encounter. The retrograde trajectory adds geometric precision to the timing mystery. Most objects in our solar system follow the same general direction of motion. Atlas cuts through this pattern at nearly perpendicular angles. The path maximizes encounters with different planetary environments while maintaining safe observational distances. Natural stellar ejection rarely produces such geometrically optimal approaches. Consider the implications of this escalating pattern. If the progression continues, the next interstellar visitor will likely be faster, stranger, and more precisely targeted than Atlas. The trend suggests we're not seeing random samples of interstellar material, but rather a systematic exploration program with increasingly sophisticated components. The inability to establish reliable baselines creates fundamental problems for planetary defense planning. How do you prepare for threats when every new example rewrites the rules? Atlas demonstrates that interstellar objects can carry exotic chemistry, follow impossible trajectories, and arrive at suspiciously convenient times. Traditional asteroid deflection strategies assume predictable compositions and well-understood physics. The progression from mysterious to mysteriously normal again could be coincidence. Statistical distributions include outliers and anomalies. 3 data points don't establish definitive trends. Each object might represent independent formation and ejection processes operating under different conditions in distant star systems. But the pattern strains credibility when examined closely. The speed increases suggest acceleration rather than random variation. The timing improvements indicate coordination rather than coincidence. The trajectory precision implies targeting rather than chance encounters. Each element has natural explanations, but the combination challenges purely random interpretation. The frequency of recent discoveries also contradicts theoretical predictions. Models based on stellar formation rates and planetary system dynamics suggested interstellar visitors would be extremely rare. The rapid succession of confirmed objects implies either flawed theoretical foundations or systematic exploration by intelligence we don't yet recognize. Atlas combines Oumuamua's acceleration mysteries with Borisov's observational advantages while adding entirely new categories of anomalous behavior. The result is an object that provides maximum scientific data while creating maximum interpretive challenges. We can study Atlas in unprecedented detail, but every measurement raises new questions about what we're actually observing. The chemical signatures alone would revolutionize comet science if they represented natural formation processes. The trajectory would rewrite stellar dynamics if it resulted from standard gravitational interactions. The timing would represent incredible fortune if it occurred through pure chance. Atlas forces us to accept either multiple statistical miracles or systematic patterns that challenge our understanding of how the galaxy operates. Researchers face an uncomfortable realization. Each interstellar visitor has exceeded expectations in different ways. The progression suggests we're not prepared for what might arrive next. Our models consistently underestimate the strangeness of these objects. Our detection networks miss them until they're already well into our solar system. Our theoretical frameworks require constant revision to accommodate new observations. The escalating anomalies pattern reveals fundamental gaps in our understanding of interstellar material behaviour and our preparation for objects that don't follow the rules we expect natural visitors to obey. Atlas has exposed a terrifying gap in our planetary defences. We're well prepared for the asteroids we can see coming, but helpless against the ones we can't. Think about how we handle conventional near-Earth objects. Take Apophis, the asteroid that briefly terrified astronomers when they calculated it might hit Earth in 2029. We tracked it for years. We refined its orbit through thousands of observations. We determined it would pass safely by our planet with room to spare. Our detection network spotted it decades before closest approach. Our computers mapped its trajectory with extraordinary precision. We had time to plan, time to prepare, time to build deflection missions if needed. The Atlas survey and other detection networks work beautifully for objects like Apophis. These systems scan the sky methodically, looking for moving dots against the star field. They're optimized for objects in predictable solar orbits that follow the same basic rules as planets and comets. Objects that return on schedule. Objects that warm up and cool down in expected patterns. Objects that behave according to gravitational physics we understand completely. But interstellar objects like Atlas operate by different rules entirely. They appear suddenly from the void between stars. They move at speeds that challenge our tracking systems. They follow hyperbolic paths our computers aren't designed to predict. These visitors don't return on predictable schedules because they never return at all. Atlas covers more distance in a single second than most commercial airliners cover in a minute. At approximately 61 kilometers per second, it moves fast enough to cross the continental United States in about 2 minutes. This speed makes comprehensive study nearly impossible during its brief passage through our solar system. More importantly, it makes deflection absolutely impossible with current technology. Consider the DART mission that successfully altered the orbital period of the asteroid Dimorphos by 32 minutes. This demonstrated that kinetic impact deflection works for slow-moving rubble pile asteroids in stable orbits around our Sun. We can nudge these objects because they're moving at reasonable speeds and following predictable paths. A small push changes their trajectory enough to miss Earth entirely. DART-style missions offer no solutions for hyperbolic interstellar visitors. These objects move too fast to intercept with existing propulsion systems. Their trajectories are one-way trips through our solar system. You can't deflect something that's already escaping at impossible speeds. Atlas is immune to capture by our Sun's gravity and guaranteed to escape no matter what we might try to do to it. The coordination challenges become even more daunting when you consider how international planetary defense protocols actually work. These systems assume months or years of preparation time. Committees meet to evaluate threats. Scientists share data across institutions. Engineers design deflection missions. Governments approve funding and launch schedules. The entire process requires extended timelines that interstellar objects simply don't provide. Atlas illustrates this timing problem perfectly. Discovered in 2025, it was already past perihelion before comprehensive analysis could begin. The limited observation window meant that most detailed studies happened after the object had already made its closest approach to our Sun and was racing back toward interstellar space. We got perhaps weeks of optimal viewing time for an object that represents our only chance to study materials from another star system. Think of it like trying to examine a bullet in flight. You might glimpse it for a fraction of a second, but detailed analysis requires stopping the bullet first. We can't stop interstellar objects. We can only watch them pass and hope our instruments capture enough data during that brief encounter to understand what we've seen. Our entire planetary defense infrastructure has a critical vulnerability that Atlas has exposed with uncomfortable clarity. We've built systems that assume threats will behave like normal solar system objects, slow enough to track, predictable enough to model, stable enough to deflect, interstellar visitors violate all these assumptions simultaneously. The detection networks that found Atlas weren't looking for objects like Atlas. The Atlas survey, ironically named considering this discovery, was designed to spot space rocks on collision courses with Earth. It happened to find something potentially far more complex than any asteroid. This accidental discovery highlights how unprepared we are for systematic detection of interstellar visitors, especially ones that might harbour hostile intent or dangerous cargo. Existing tracking systems work by comparing images taken hours or days apart, looking for objects that move against the background stars. This approach works well for near-Earth asteroids that follow predictable paths and maintain roughly constant brightness. But interstellar objects can change brightness dramatically as they outgas. They can fragment unexpectedly. They can exhibit acceleration that doesn't match gravitational models. These behaviors confuse automated detection algorithms designed for conventional asteroids. The rapid passage of interstellar objects also means we have minimal time to verify their properties and assess potential threats. With conventional asteroids, we can observe them through multiple orbits, refining our understanding of their size, composition, and structural stability. Interstellar visitors give us one chance to get the observations right. Miss important details during that brief window, and we may never have another opportunity to study them. International protocols for handling threatening objects assume we'll have time to debate response options. Scientists present evidence to government committees. Politicians weigh costs and benefits. Military leaders assess deflection strategies. This deliberative process works well for conventional threats that provide years of warning time. Interstellar objects might provide only weeks or days between detection and closest approach, making careful deliberation impossible. The communication challenges become equally problematic. How do you inform the public about a potentially threatening interstellar object without triggering panic? How do you coordinate international response when the object might pass by before diplomatic processes can establish joint action? How do you make life or death decisions about planetary defense with incomplete information and minimal preparation time? Atlas also reveals gaps in our understanding of what constitutes a threat from interstellar space. We've developed expertise in assessing asteroid impact risks based on size, composition, and approach geometry. But interstellar objects might carry threats we've never considered. Exotic materials that behave unpredictably during atmospheric entry, biological contamination from alien environments, technologies designed to appear natural while carrying out surveillance or worse missions. The statistical reality provides some comfort. The likelihood of a threatening interstellar object remains extremely low compared to conventional asteroid risks. We catalogue thousands of near-Earth asteroids that could potentially impact our planet. Only 3 confirmed interstellar visitors have passed through our solar system in recorded history. The numbers favour conventional threats over exotic ones by overwhelming margins. But the potential consequences of an interstellar impact could be far more severe than conventional asteroid strikes. These objects move at speeds that would release devastating amounts of energy during collision with Earth. Their unknown compositions might include materials that create unprecedented destruction during impact. Their potential artificial nature might mean we're dealing with deliberately targeted weapons rather than random cosmic accidents. The gap in our defences isn't just technological, it's conceptual. We've built planetary defense systems around the assumption that space threats will behave according to familiar rules. Natural objects following predictable orbits with compositions we understand and properties we can model accurately. Interstellar visitors challenge every one of these assumptions simultaneously. Think of it like designing coastal defences for ocean waves, then discovering that some waves can fly. Your seawalls and breakwaters work perfectly for normal threats, but become completely useless against attack vectors you never considered possible. That's essentially what Atlas has done to our planetary defense planning. It's revealed that our most carefully designed protections might be irrelevant against the threats that matter most. The defense network's blind spot isn't necessarily fatal. We're still far better protected against cosmic impacts than any previous generation in human history. We can detect and deflect the vast majority of threatening objects in our local neighbourhood. Our systems work extremely well for the kinds of threats they were designed to handle. But Atlas forces us to confront uncomfortable questions about the threats we haven't designed our systems to handle. Fast-moving visitors from other star systems that follow no rules we recognise. Objects that might carry technologies or biological materials completely outside our experience. Visitors that could reshape our understanding of what's possible in the universe, while simultaneously demonstrating our helplessness to respond to genuinely novel challenges. The real work of planetary defense continues to focus on cataloguing and tracking ordinary near-Earth asteroids, because these represent the most statistically probable threats to our civilization. The greatest danger still comes from familiar neighbours rather than exotic visitors. But Atlas has shown us that our preparations for the familiar might leave us completely vulnerable to the genuinely unknown. While this gap is real and concerning, it shouldn't overshadow the remarkable success of our existing planetary defense systems in handling conventional threats. But it should motivate us to expand our capabilities and our thinking to encompass possibilities we've barely begun to consider. While speculation runs wild about alien probes, the scientific community is treating Atlas as something far more valuable, a pristine sample from another star system. Scientists approach Atlas like archaeologists examining an ancient artifact. Every measurement matters, every spectral line tells a story. The James Webb Space Telescope revealed that 8:1 carbon dioxide to water ratio. That extreme imbalance challenges every model we have for how comets form naturally. But instead of jumping to extraordinary conclusions, researchers ask what this chemistry tells us about stellar formation environments we've never seen. The methodical approach contrasts sharply with sensational theories. While conspiracy videos multiply across social media, astronomers coordinate observations between Hubble, James Webb, Mars probes, and the JUICE spacecraft. They're positioning every available instrument to study Atlas safely from a distance. This represents the largest coordinated observation campaign for an interstellar visitor in human history. Consider what Atlas's chemistry actually reveals about conditions beyond our solar system. The carbon dioxide dominance suggests formation in regions where CO2 ice was abundant and water was scarce. That's the opposite of what we see in our local environment. Atlas carries chemical fingerprints from stellar formation processes that operated under completely different rules than the ones that created our sun and planets. The nickel emissions without accompanying iron create another puzzle piece. In nature, these elements forge together in supernovas. They travel together through space. They appear together in meteorites and asteroids throughout our solar system. Yet Atlas somehow releases nickel while keeping iron locked away. This separation suggests formation processes or storage mechanisms that don't exist in our neighbourhood of the galaxy. Think of Atlas like a message in a bottle that drifted across an ocean we've never explored. The bottle itself tells us about the materials available on distant shores. The contents reveal conditions that shaped those far-off environments. Each chemical signature provides clues about stellar formation in regions where physics operated under different constraints than the ones we observe locally. Atlas's thick disk origin provides a window into galactic evolution. The thick disk contains stellar populations that formed over 10 billion years ago, when our galaxy was still assembling itself from smaller structures. Conditions back then were radically different from today's orderly spiral arms. Star formation was more violent, heavy elements were scarce, planetary systems formed under constraints that no longer exist in our cosmic neighbourhood. This makes Atlas a unique time capsule carrying information from the galaxy's infancy. Its chemistry preserves records of conditions that existed billions of years before Earth formed. Like finding a fossil that predates all known life forms, Atlas expands our understanding of what was possible in the early universe. The observational challenges are immense. Atlas moves faster than any object we've studied before. It's already passed its closest approach to the Sun. The observation window closes rapidly as it races toward the outer solar system. Scientists have only months to gather data that might take decades to fully analyze. Multiple space agencies coordinate their instruments to maximize data collection. Mars-orbiting spacecraft provide observations from a different angle than Earth-based telescopes. The JUICE mission, currently traveling toward Jupiter, offers another perspective as Atlas passes through different parts of our solar system. Each viewpoint adds layers of information about composition, structure, and behavior. The speed itself creates scientific opportunities alongside observational challenges. Atlas's velocity of 60 kilometers per second means it experiences extreme conditions during its solar approach. The rapid heating and cooling cycles create controlled experiments in material science. Researchers can observe how exotic ices behave under temperature changes that would take months to reproduce in laboratory settings. Scientists can't launch a dedicated mission to intercept Atlas. The combination of speed and late discovery makes such missions impossible with current technology. By the time spacecraft could be designed, built, and launched, Atlas would already be racing beyond Neptune's orbit. The energy requirements to match its trajectory exceed anything humanity has achieved in space exploration. This limitation forces researchers to make the most of remote observations. Every spectral measurement becomes precious. Every photograph carries data that can't be replaced. The scientific community treats Atlas like a rare astronomical event that might not repeat for generations. The systematic approach reveals how scientific methods handle extraordinary claims. Researchers test Atlas's unusual properties against known natural processes before considering more exotic explanations. The 8:1 CO2 ratio is unprecedented, but it could result from formation in protoplanetary disks with unusual compositions. The nickel without iron is mysterious, but it might indicate chemical separation processes that operate under extreme conditions. Each anomaly represents a potential breakthrough in understanding interstellar chemistry. Atlas challenges existing models of comet formation, stellar evolution, and galactic chemical distribution. Whether these challenges lead to revisions of established theories or discoveries of entirely new processes, the scientific value is enormous. The thick disk connection adds another layer of significance. Most comets we've studied come from our local Oort cloud, formed alongside our solar system. Atlas originates from stellar populations that existed when the galaxy was fundamentally different. It carries chemical signatures from an era when star formation followed rules we're still trying to understand. This temporal perspective transforms Atlas from a simple comet into a messenger from deep time. Its composition preserves information about galactic conditions that existed long before our sun ignited. Like reading pages from a book written in a language we're still learning to decode, Atlas offers insights into cosmic history that we can't obtain any other way. The coordination between different observatories demonstrates science at its best. International collaboration overrides political boundaries when faced with time-sensitive discoveries. Researchers share data immediately rather than hoarding it for competitive advantage. The Atlas observation campaign represents humanity working together to understand phenomena that transcend individual nations or institutions. Ground-based telescopes track Atlas's trajectory and monitor changes in brightness and emission patterns. Space-based instruments analyze its chemical composition and internal structure. Planetary probes provide observations from multiple angles as Atlas moves through different regions of our solar system. Each platform contributes unique capabilities to the overall scientific effort. The data collection process resembles detective work more than theoretical speculation. Scientists gather evidence systematically. They document observations carefully. They test hypotheses against multiple independent measurements. Every conclusion must survive peer review and replication by other research teams. Atlas's true value lies not in confirming dramatic theories about alien technology, but in expanding our understanding of how planetary systems form across the galaxy. Its unusual chemistry teaches us about stellar environments that operate under different rules than our local region. Its extreme speed demonstrates that interstellar objects can maintain coherent trajectories across vast distances and timescales. The scientific windfall from Atlas will continue long after it disappears into deep space. Years of analysis await for the data already collected. Computer models will test various formation scenarios against the observed chemical signatures. Theoretical physicists will explore what conditions could create the unusual elemental ratios that Atlas displays. Future interstellar visitors will benefit from lessons learned during the Atlas observation campaign. Detection networks will be better prepared to spot fast-moving objects earlier in their approach. Observation protocols will be refined based on what worked and what didn't during this unprecedented international effort. Theoretical models will incorporate the new data about interstellar chemistry and formation processes. The methodical approach to studying Atlas provides a template for handling future encounters with the unknown. Rather than rushing to sensational conclusions, the scientific community demonstrates how to balance healthy skepticism with genuine curiosity. Every measurement is valuable. Every observation contributes to the larger picture. Every theory must earn its place through evidence rather than speculation. Atlas represents the kind of discovery that reshapes our understanding gradually rather than dramatically. Like continental drift or DNA structure, its significance will become clear through careful study over time. The immediate impact lies not in confirming extraordinary theories, but in providing new data that challenges existing models and opens previously unexplored questions. The observation campaign itself becomes part of the scientific legacy. Future researchers will study not only Atlas's properties, but also how the international community responded to this unprecedented opportunity. The coordination between nations, institutions, and instruments demonstrates what becomes possible when humanity focuses its attention on understanding rather than speculation. As Atlas races beyond our ability to observe it directly, the real work begins. Analysis of the collected data will continue for years. Each spectral line will be examined for clues about interstellar formation processes. Each photograph will be searched for details that reveal how exotic materials behave under extreme conditions. The scientific method proves its value through cases like Atlas. Extraordinary claims require extraordinary evidence. Unusual observations demand careful analysis. The universe contains genuine mysteries that reward patient investigation more than hasty conclusions. Atlas teaches us that the most profound discoveries often come through methodical study rather than dramatic revelations. Atlas won't be our last interstellar visitor, and the next one might not pass by so safely. Here's what we're doing to prepare. 3 confirmed interstellar objects in less than a decade suggest something fundamental about our galaxy. Either we're witnessing remarkable coincidence, or these visitors are more common than we thought. The pattern creates urgency around a simple question. What happens when the next hyperbolic object isn't content to just observe? Our detection networks need complete overhaul to spot fast-moving objects earlier. The Atlas survey that discovered this visitor operates on timescales designed for slow asteroids, not objects moving at 60 kilometers per second. Current telescopes scan the sky in patterns that assume predictable orbits. Interstellar visitors don't follow those rules. The Vera C. Rubin Observatory represents our best hope for early detection. Its wide field of view can capture more sky in single images. Rapid survey cadence means shorter intervals between observations. These improvements help, but they're still designed around conventional asteroid behaviour. We need detection systems that assume the unexpected has already happened. Think of it like earthquake monitoring. Seismometers detect tremors hours before major events. We need space-based sensors that can spot trajectory anomalies while objects are still beyond Neptune's orbit. Early warning provides time for proper analysis, instead of scrambling to understand visitors that are already leaving. Technological developments require massive investment in faster response systems. Current space missions take years to plan and launch. Interstellar objects provide weeks of optimal observation time. We need spacecraft that can deploy within days, not decades. Rapid deployment observation systems would work like emergency response networks. Pre-positioned telescopes that can redirect toward unexpected targets. Communication satellites that relay high-resolution data in real time. Robotic probes stored in launch-ready configurations waiting for activation. The European Space Agency's HERA mission shows what's possible when we plan for specific events. It will study the aftermath of the DART impact on asteroid Dimorphos. This focused approach works for predicted encounters. We need similar systems that can activate for unpredicted ones. International coordination becomes critical when observation windows last only weeks. Different countries own telescopes with different capabilities. Some excel at chemical analysis, others provide high-resolution imaging. Coordination protocols must enable rapid data sharing without bureaucratic delays. The challenge resembles wildfire response. Multiple agencies with specialized equipment must coordinate instantly. Air tankers, ground crews, and command centers work together because the protocols exist before the emergency begins. We need similar systems for space-based threats. Current asteroid tracking relies on voluntary data sharing between observatories. That works fine for objects discovered years before close approach. It fails completely when discovery and analysis must happen simultaneously. We need mandatory sharing protocols backed by international agreements. Communication protocols require delicate balance between transparency and panic prevention. The public deserves accurate information about potential threats, but premature speculation can create mass hysteria that complicates actual response efforts. The 2029 flyby of asteroid Apophis provides a test case for public communication. It will pass closer to Earth than communication satellites. No impact risk exists, but the proximity creates opportunities for fear-based misinformation. How we handle Apophis communication sets precedents for more ambiguous situations. Atlas demonstrates the problem perfectly. Its unusual chemistry and mysterious behaviour fuel speculation about alien probes. Scientists must address these theories without dismissing legitimate questions. The goal is creating informed public discussion rather than silence or sensationalism. Scientific preparation means developing better models for interstellar object composition and behaviour. Each visitor teaches us that our assumptions need constant revision. Natural formation processes in other stellar systems create chemistry we don't recognise. Materials science under extreme conditions produces structures we haven't seen before. Laboratory experiments can simulate some interstellar conditions, high-energy particle bombardment over extended periods, chemical reactions at temperatures near absolute zero, pressure environments that don't exist anywhere in our solar system. These tests help distinguish between natural and artificial signatures. Computer modelling advances allow simulation of billion-year journeys through interstellar space. We can test how different materials respond to cosmic ray exposure. Model trajectory changes from gravitational encounters with multiple star systems. Predict chemical evolution during extended deep freeze conditions. The success of the DART mission proves we can deflect slow-moving asteroids through kinetic impact. But those techniques assume months of preparation time and predictable orbital mechanics. Hyperbolic interstellar objects provide neither advantage. New deflection strategies must account for extreme velocities and unpredictable compositions. Nuclear pulse propulsion could theoretically alter trajectories of fast-moving objects. Solar sail arrays might redirect smaller visitors through radiation pressure. Gravity tractor spacecraft could influence paths through prolonged gravitational interaction. Each approach requires technologies that don't currently exist in deployable form. Nuclear pulse systems need miniaturization for rapid deployment. Solar sails require materials that can survive high-velocity particle impacts. Gravity tractors must operate at distances where communication delays measure in hours. The long-term perspective reveals why each interstellar visitor matters regardless of its true nature. Atlas teaches us about detection limitations, international coordination challenges, and public communication protocols. These lessons apply whether future visitors are natural objects from exotic stellar environments or artificial probes from advanced civilizations. Pattern recognition becomes crucial as more interstellar objects appear. If they're natural, we learn about galactic diversity and stellar formation processes. If artificial, we establish protocols for peaceful contact or defensive responses. Either way, systematic study builds knowledge that prepares us for whatever comes next. Statistical analysis of interstellar visitor characteristics creates baseline expectations. Size distributions, velocity ranges, chemical compositions, and trajectory patterns establish normal parameters for natural objects. Deviations from these baselines become easier to identify and investigate properly. Atlas's extreme velocity and unusual chemistry expand our definitions of what's possible. Future visitors might show even more exotic properties. By documenting each encounter systematically, we build databases that help distinguish between natural extremes and truly anomalous behavior. The timescales involved demand patience and sustained investment. Interstellar objects appear unpredictably with observation windows lasting weeks. Proper study requires maintaining expensive detection networks and rapid response capabilities, even during long periods without visitors. This resembles forest fire preparedness. Equipment sits unused for months or years, then must perform perfectly during brief critical periods. The cost seems wasteful until the emergency arrives. Then, adequate preparation makes the difference between controlled response and catastrophic failure. Educational initiatives help create informed public understanding of space-based risks. Most people overestimate the danger from dramatic low-probability events, while underestimating mundane, high-probability threats. Asteroid impacts capture imagination, but statistical risk remains extremely low compared to conventional natural disasters. The goal is calibrated concern rather than either complacency or panic. Asteroid impact represents genuine existential risk that deserves serious preparation, but that risk must be weighed against more immediate threats that require resources and attention. Atlas provides practice for thinking clearly about cosmic risks. Its mysterious properties generate speculation, but evidence remains limited. Learning to separate fascinating anomalies from genuine threats builds intellectual discipline that applies to future encounters. While we can't defend against every possible scenario, each interstellar visitor makes us more prepared for the next one. Atlas reveals specific weaknesses in our detection and response capabilities. Those weaknesses become priorities for improvement while we wait for the next hyperbolic visitor to appear. The improvements benefit conventional asteroid defense as well. Faster detection, better international coordination, and clearer communication protocols enhance our response to all space-based threats. Atlas's visit catalyzes advances that protect us from multiple directions. Whether Atlas represents ancient technology or exotic natural processes, it succeeds in its most important mission, making us better observers of the cosmos and more thoughtful guardians of our own world. After examining all the evidence, the most dangerous thing about Atlas isn't what it might be. It's how it reveals our tendency to fear the spectacular while ignoring the mundane. While we spend months debating whether Atlas carries ancient alien technology, thousands of ordinary asteroids drift through space on paths that could actually threaten Earth. These conventional near-Earth objects pose real, measurable risks that we can calculate and prepare for, yet they rarely capture headlines or spark public imagination the way mysterious interstellar visitors do. The numbers tell a clear story. We're far more likely to face a threatening conventional asteroid than a hostile interstellar visitor. Near-Earth asteroids outnumber confirmed interstellar objects by thousands to one. Most of these space rocks follow predictable orbits that our detection networks can track for decades in advance. We know where they're going and when they'll arrive. Atlas represents statistical noise compared to the steady drumbeat of potential asteroid impacts. Every few months, small asteroids burn up in our atmosphere. Every few years, larger ones create spectacular meteor events. Every few decades, city-killer-sized objects pass uncomfortably close to Earth. This regular pattern of cosmic bombardment continues regardless of whether mysterious visitors from other star systems happen to be passing through our neighbourhood. Consider how the Apophis case study demonstrates proper risk assessment. When astronomers first calculated this asteroid's orbit, they found a small but significant chance of Earth impact. Instead of speculation or panic, they organised systematic observation campaigns. Multiple telescopes tracked Apophis across several years. Each new measurement refined the orbital calculations. The initial uncertainty gradually resolved into clarity. Apophis won't hit Earth during its close approach. Careful observation and mathematical analysis eliminated the threat without drama or conspiracy theories. The asteroid became a success story for evidence-based evaluation rather than a source of ongoing fear. Apophis teaches us how to think about cosmic risks. Start with what you can measure. Gather more data when uncertainty exists. Update your assessment as new information becomes available. Don't let initial concern turn into permanent anxiety when evidence shows the threat was overstated. Atlas fails this test of proper risk assessment. Instead of treating it as an interesting scientific anomaly, some observers jump to extraordinary conclusions based on limited data. The unusual chemistry becomes evidence of alien engineering. The precise trajectory suggests deliberate targeting. The fragmentation pattern indicates controlled deployment of surveillance systems. These interpretations reveal more about human psychology than alien technology. We're pattern-seeking creatures who find intentional design in random events. We prefer exciting explanations over boring ones. We fear the unknown more than the familiar, even when the familiar poses greater actual danger. The public education challenge becomes clear when you compare media coverage of Atlas versus conventional asteroids. Stories about potential alien probes generate millions of views and countless shares on social media. Detailed reports about asteroid tracking and deflection research struggle to find audiences. The spectacular crowds out the essential. This attention imbalance creates real consequences for planetary defense. Resources follow public interest. Funding flows toward projects that capture imagination rather than those that address practical threats. Politicians respond to constituents who worry about alien invasions, not those concerned about statistical asteroid risks that won't materialize for decades. Sensational theories about interstellar visitors can distract from unglamorous but necessary work. Building better detection networks requires sustained investment in ground-based telescopes and space-based sensors. Developing deflection technologies demands patient engineering and repeated testing. Training international coordination protocols needs diplomatic persistence across multiple governments. None of these essential activities generate the excitement that mysterious interstellar objects create. Yet they represent our best defense against threats that statistics suggest we will eventually face. Every dollar an hour spent chasing alien probe theories is a dollar an hour not invested in practical planetary protection. The distinction between genuine threats and fascinating mysteries matters more than most people realize. Genuine threats require immediate action and resource allocation. Fascinating mysteries deserve scientific study, but shouldn't drive policy decisions or defense spending. Conflating the two categories leads to poor preparation for actual dangers. Think of it like emergency preparedness for natural disasters. You might find volcanic eruptions more interesting than house fires. Volcanoes create spectacular displays and reshape entire landscapes. House fires seem mundane by comparison. But you're thousands of times more likely to experience a house fire than a volcanic eruption. Smart preparation focuses on smoke detectors and fire extinguishers, not volcano evacuation plans. Atlas serves as a test case for our ability to maintain this distinction. The object exhibits genuinely unusual properties that deserve scientific investigation. Its chemistry differs from known comets. Its trajectory seems remarkably convenient for observation. Its behavior patterns challenge existing models of interstellar object physics. These anomalies make Atlas scientifically interesting without making it threatening. Unusual doesn't equal dangerous. Rare doesn't equal hostile. Ancient doesn't equal artificial. Each of these logical jumps transforms scientific curiosity into unfounded fear. The evidence-based approach treats Atlas as a natural phenomenon until proven otherwise. This doesn't mean dismissing unusual properties or avoiding difficult questions. It means requiring extraordinary evidence for extraordinary claims. It means testing alternative explanations before accepting radical ones. Atlas could represent exotic natural chemistry from stellar formation environments, unlike our local region. The unusual composition might indicate processes we haven't studied because they don't occur in our solar system. The precise trajectory could result from gravitational interactions we don't fully understand because they operate over billion-year timescales. These natural explanations require us to expand our scientific understanding without abandoning scientific methodology. They challenge our models of comet formation and interstellar dynamics. They force us to consider chemical processes and orbital mechanics that operate under conditions we've never observed directly. But natural explanations don't make Atlas less significant. If anything, they make it more valuable for advancing human knowledge. A genuine sample of interstellar material formed under alien stellar conditions would revolutionize our understanding of planetary system formation across the galaxy. The psychological appeal of artificial explanations reveals something important about how humans process uncertainty. We prefer intentional agents over impersonal forces. We find comfort in intelligence, even hostile intelligence, rather than pure randomness. A universe where aliens visit Earth feels more comprehensible than one where exotic chemistry emerges from processes we don't understand. This preference for agency over mechanism influences how we interpret ambiguous evidence. Patterns that could result from natural processes become evidence of design. Coincidences that could occur through chance become proof of intention. Unusual properties that could indicate unknown physics become signatures of unknown technology. Atlas challenges us to resist these psychological biases and evaluate evidence objectively. The stakes extend beyond one mysterious object. Our response to Atlas establishes precedents for how we'll handle future interstellar visitors. If we let speculation override systematic investigation, we'll be less prepared for whatever comes next. The real threat assessment acknowledges both possibilities while prioritizing based on evidence and probability. Atlas might represent alien technology that transforms our understanding of intelligence in the universe. More likely, it represents natural processes that expand our knowledge of chemistry and physics under extreme conditions. Either outcome justifies continued scientific study. Neither outcome justifies diverting resources from conventional planetary defense or treating Atlas as an immediate threat to human civilization. The distinction between interesting and threatening remains crucial for making smart decisions about cosmic risks. Atlas's greatest contribution may be teaching us how to think clearly about these distinctions, how to separate scientific anomalies from existential threats, how to maintain curiosity without succumbing to fear, how to prepare for statistical probabilities while remaining open to extraordinary possibilities. The next time an interstellar visitor appears in our telescopes, we'll have Atlas as a reference point. We'll know that unusual chemistry and precise trajectories can occur through natural processes. We'll understand that mysterious doesn't equal threatening. We'll be better equipped to evaluate evidence systematically, rather than jumping to dramatic conclusions. This measured approach serves humanity better than either complacency or panic. Complacency ignores real risks that statistics tell us we'll eventually face. Panic wastes resources on imaginary threats while neglecting practical preparations. Evidence-based evaluation finds the middle path between these extremes. Atlas demonstrates that the universe contains wonders we don't yet understand. Some of those wonders might be technological, most will be natural, all deserve careful study. None should distract us from preparing for the cosmic risks that probability suggests pose the greatest actual danger to our long-term survival. Atlas isn't the alien probe some fear it might be, but it's something equally profound. A reminder that the universe still holds mysteries that challenge our assumptions and expand our perspective. Whether Atlas represents ancient technology or exotic natural processes, it's already succeeded in its most important mission, making us better observers of the cosmos and more thoughtful guardians of our own world. The next time an interstellar visitor appears in our telescopes, we'll be ready with better instruments, clearer thinking, and the wisdom that the most extraordinary explanations aren't always the most likely ones.